All right, ready?
All right, good morning, everybody. Welcome to Thursday at the 4th Jack Eddy Symposium. We will be skipping over the working group reports this morning since we have larger working groups tomorrow. So it is now my pleasure to introduce our morning keynote speaker, who's Vladimir Arapetian from NASA Goddard Space Flight Center, who will be talking to us about the Sun-Earth system in time, searching for habitable planets. Come on up, Vladimir.
Hello, everybody. So, today I'm going to talk about young science that probably younger than half of the participants, and it's emerging interdisciplinary science. And you can see my collaborators. It's only the part of the collaborators. The team of superheroes. Some of the superheroes are in this room, and I would say that. It needs a team of superheroes, so it takes a village, to approach the science. And today I will try to introduce the basically major concepts that how we can go ahead with the science, with the open science, with the open tools. Next slide, please. Yeah, so we're going to discuss this.
Forward and reverse.
Oh, thank you very much. Yeah. So we're going to talk about these issues like is Earth a unique planet? Because we're talking about exoplanets, right? We're searching for habitable worlds. It's one of the most amazing endeavors of civilization, and we're trying to find like us or something like us, or not exactly like us. What are we looking for? So that's what would be the major theme of and how we can apply the tools to successfully move forward. So then we talk about when we talk about a planet, it's not about a planet, it's the family. It's a family star and a planet, and they shape each other. Well, basically, star shapes the planet mostly. And then we talk about the super flares and the impact of the super flares on exoplanetary climate, and how we can validate some of those models, and how we can create and derive some chemical signatures of young prebiotic planets in the era of JWST via laboratory experiments. So I will start with the I don't know how to animate, how to create this animation. Should I? What this? Oh, what? No, see, I don't know how to. Because I thought that we we're gonna have a laptop, so there is an arrow to animate this. Oh, it's going. Oh yeah. Thank you. Yeah. Now let's see. No. But somebody should click on, because I have no control. I'm sorry. Yeah, so what you see here, since 1995, when the first habitable planet, not habitable, just first extrasolar planet was discovered, okay? And so we have now over 5,500, and actually exactly 5,535 exoplanets, as of today, and around 10,000 in the phase of confirmation. So we have a huge number of those creatures that we don't understand. And it's interesting that you can see that this is our solar system right here. It's a pretty big system, right? Several astronomical units. So, but you see that most of the systems are really compact, really small. And so most of the stars are not like our sun. They're much smaller, and much less luminous, but not necessarily less flaring, less magnetically active. So the point is, imagine that this is the situation if you take our planet and move 20, 30 times closer to the sun. Okay, so, and we know that how sun works. We talked about space weather. Now imagine how our civilization will feel under this kind of, even a quiet sun, I would say, at a distance, well, not only hot, but also a lot of ionizing radiation. So, and what will it do to the atmospheric escape, to the atmospheric evolution of a planet? So the one hint that we can get about the atmospheric escape comes from this gap. Oh, no, sorry, that's the next slide. Yeah, so basically, like, unfortunately, I couldn't animate it, but you see from here, that we have the planets from, planets smaller than Earth, the planets greater than Jupiter, temperature range are the very cold planets, like less than 200 degrees Kelvin, all the way to 1250 lava planets. So we have a great variety that creates a great physics that can be explored, to understand the planetary formation, planetary evolution. So that this plot shows the relationship between the orbital period and planetary ranges in the Earth radius. So this is the Earth-like planet. You see that we have a number of them. So as of today, it's about 200 exoplanets are Earth-like, okay, and much more exoplanets that are really weird. This so-called the super Earth that we don't see here in our solar system. We don't understand why we don't see it. But one hint to the whole problem of exoplanetary science comes from this. See that? There is a gap. There is a really, practically absence of exoplanets, while it's so easy observationally to find them. So it's not an observational bias. It's really physical situation, meaning that, planets are not there. They don't show any basically, so we need to understand that. That probably has something to do with the planetary evolution and atmospheric evolution. So, in order to, so the question is that you see that how messy the situation is. Now, in that mess, we need to find, and that's our primary goal, right? Extra goal of our civilization, to find a habitable planet. So I call it sweet spot of habitability, because first we need to understand what the habitability is, what contributes to the different factors. So here I have the Venn diagram that basically describes what we need to look for. First, we need to understand, because we know. Let's go to the basics. The basics says that life on Earth started very early, as soon as conditions allow to start it. So that means that if I wanna for life, I wanna start to probably go for the rise of life, for the rise of habitability. So right. So therefore, I want to start with the to specify and to characterize the space weather magnetic activity from young solar analogs, and we're lucky that we have a few of them actually close by that can be studied by the flotilla of different space missions and ground-based telescopes to understand. To understand the flares, coronal mass ejections, and possible energetic particle events that would contribute, and stellar winds, of course. So that's what contributes to the space weather. And then, we need to combine this research to study, to apply the open tools to study the rise of the primary atmosphere, some of the geophysical models, magma ocean, mantle convection, volcanic activity, atmospheric escape, because we know now that looks like that we're all volcanic creatures, and the atmosphere has a volcanic origin. So we have a lot of molecular nitrogen in the atmosphere, 77%, and this is the most geochemically stable gas, and it probably was around 4.5 billion years ago. So, and the CO2 was one of the prevailing gases, that time. Now we have a weird situation with 21% of oxygen, and I'll touch upon that. So basically, and the third process is atmospheric and prebiotic chemistry. So we need to study how, how the space weather affects chemistry, how space weather affects atmospheric evolution. And after we understand that, the sweet spot will give us the what are the best conditions, for the rise of habitability. I'm not even talking about habitability because, as you can see here, so therefore that opens up that the atmospheric escape is a gateway to atmospheric evolution. So, and you can see here, so atmospheric escape, is driven by the XUV fluxes, thank you very much. Yeah, driven by X-ray emission, extreme UV emission, at the same time driven by the Poynting fluxes from the CMEs and energetic particles, creating Joule heating. We have two sources that need to be evaluated for different conditions because the heating creates a different kind of atmospheric escape, and this shows that that depending on whether the planet is magnetized or unmagnetized, you can have the whole thermal escape. This is the simplest one. Probably for our Earth is even for our Earth during the active sun, the so-called ion escape is the important thing. Photochemical escape, thermal hydrodynamic escape. And so we have different types of escape, and there need to be evaluated. That's this work already been started several years ago, and we already have some hints, how to move in that direction. Because every time you see a solar flare, you see that our ionosphere normally it loses about 3 kilograms of oxygen per second, and during big flare it loses about 10 kilograms per second. Okay, so and that's the quiet sun. But imagine again moving a planet 30 times closer. All the fluxes should be multiplied by a factor 30 square. We talk about 1,000 times greater, so multiplied by 1,000 times. So therefore, we need to create those models to scale up this atmospheric escape. So therefore, it comes to the question: is the Earth is a unique planet? So I want to discuss that first, philosophical question, but it can be discussed from scientifically. And is a science system is a unique system? Should we ask about the Earth, or we ask not about the system? So basically, the answer is, as I will show in a minute, that we need to ask a question: is a science system is a unique system? Do we need to bring the sun into the picture, and why? So the answer to this question, let's look at the evolution of our sun in time. So this is our sun, young sun, less than 300 million years ago. It's a really crazy sun that shows flares at the rate of, from one super flare. I'm talking about 10 to the 34 ergs. It's about 100 times bigger than the largest flares observed in the space era. At the rate of one super flare per few days. So, and a lot of star spots, okay? So, and imagine that, how can you live that, close by, and what the conditions for a planet to be lucky enough to retain the atmosphere and then go ahead with it and then develop life. Okay, so this is the whole process that needs to be investigated, and see that we go from the very active star to very, the pretty quiet star, and that's how the planets responded to this atmosphere, to the evolution of our sun. See that, for instance, normally we talk about so-called habitable zone that everybody knows about it, right? The zone where the Goldilocks zone, where it's not too hot, no, it's not too cold, right? So we're now there. That's the conditions for habitability. It's not that easy. Habitable zone doesn't exist because habitable zone is zero approximation. It's a 0D, zero dimension, because it's not. Instead, we have the habitable transition, habitable phase. And look what happened to our Earth and all planets. When the sun 4.5 billion years ago had 25 to 30% less bolometric luminosity, which means that our Earth was supposed to be an icy ball, but it wasn't the case. First, it probably was, but then wasn't the case due to some kind of a greenhouse gas. So we need some factor that can create so-called global warming at that time, the so-called faint Young's paradox. At the same time, because Venus was so close, okay, at 0.7 AU multiplied square squared gives you a factor of 2 greater. So Venus, that time when we were in a bad shape, Venus was in a great shape like we are today. Okay, so even biometrically speaking, and Mars was in terrible conditions, because being at 50% further away square, it was receiving twice less energy. Venus was receiving twice more energy, and we were receiving, with respect to us, I'm talking about. And see that what happened. So we started really hot in the accretion phase, and then we got solidified. Earth moved into the habitable state, and then a habitable state, and then you see those things. It's so-called ice periods and ice phases and hot phases, and it's still going on because of the carbon cycle and because of the geophysics and the change of the land-sea fractions. But still, we're in the habitable state. But at some time, we're going to go out of it. Why? Because we know that the sun becomes 10% more luminous every billion years. So in 1 billion years, we're going to have 10 times 10% more luminous sun, and the climate models can show you that the oceans will start boiling. So forget about it. But there is even worse news. So the worst news is that as Earth becomes older, the outer core gets cooler and cooler, so Earth will lose magnetic field. So that shows that all planets go through the habitable phases. Okay, so that also shows that if we're looking for so-called Earth 2.0, what kind of Earth are we talking about? Are we talking about the so-called Hadean Archean Earth, when Earth didn't have oxygen at all? And then at some point it didn't have oxygen at all, but it had a lot of methane at the level of 1,000 parts per million, because of the rise of methanogens, all those creatures that knew how to get energy. And then advent of the photosynthetic life that's much more efficient, that started to pump in the oxygen into the atmosphere. And even now, if you look at 500 million years ago, so the amount of oxygen varied from 5% to 20%. So what kind of Earth are we looking at? So this is the picture that we need to follow. We need to study the impact of the space weather of CME, flare, and the wind and the energetic particles, on all subsystems of our planet as the point number one, to the early sun, the early Earth as a point number two, and then exoplanets and many other points, like 200 points. So this is the portrait of our sun, from Kepler Space Telescope. You see of the young sun. So you see this is the star spots, in the red, and blue are super flares. You see how numerous they are. It's 1 year, 2nd year, 3rd year, and 4 years of observations. So you see this particularly high super flares. They're pretty frequent, and they should be accounted for when we look at the atmospheric evolution. So what we're doing, we're looking for the coronal mass ejections. We know the flares exist. We know that the coronal mass ejections come with the coronal, super flares from the sun come with the coronal mass ejections. We want to find those stellar coronal mass ejections. So we already have plenty of cases, few tens of cases, using the those coronal mass ejections are important for the exoplanetary evolution, and also for the understanding the angular momentum loss of the stars. So basically, the two ways to do it: by looking at the prominence eruptions that basically normally accompany the coronal mass ejections, as we learned from our sun as a star. So that's the one way observationally. Look for the blue shifted Balmer lines on those stars. And another way is to look for the XUV dimming. It's when the huge mass, the flux rope, leaves the corona. It basically creates the void, reduction of the density and reduction of the flux for about a couple of hours, like here, you see here. Okay, so if we can find a couple of signatures, and we did find in the paper that will probably come out later this month. So yeah, and sorry. So this is the case of the of our one of the CME we found, from the young solar analog. It's only 125 million year old star that flares like crazy and shows, both signatures of X-ray dimming and the blue shifted emission. So therefore, in order to meaningfully understand that, we need to basically first to understand, the portrait, to get the magnetic skeleton of the young sun, then its magnetic structure, to understand whether we can reconstruct X-ray corona. That's our main validation, and that will give us more, more the validation for the reconstruction of the stellar wind, and then insert the magnetic flux rope, and with the energy of the 10 to 34 for a super flare, and run a super flare. So this is one of the models, the work in progress, and Monk Jean is leading this together with our team. So if you can you run please the simulation quickly? So this you're looking at the equatorial plane of the sun. You're looking from north to the star. This is the half AU. Total is 1 astronomical unit by 1 astronomical unit. The Earth is somewhere here. So this is the halfway through. Unfortunately, can you run it? It's not playing. Well, should be playing. Oh, well, it did play. Okay, so anyway, for the sake of time, might be later. Yeah, sure. But it does work normally. I don't understand why not. Anyway, oh yeah, it does work. So okay, so you see that this ejection of the flux rope creating shocks, and those shocks propagating first at 5,000 kilometers per second, and basically decelerating to about 3,000 kilometers per second. This kind of CME resembles one of the biggest super flare events from the current sun, so-called 775 AD event. So then the CMEs propagate out, and they create shocks, and those shocks, as the particles cross the shock front, they go back and forth into the Fermi one acceleration. They gain energy. So we are basically coupling the kinetic model with the MHD model in order to calculate. So this is the impact on the CME of the early Earth that basically disturbs the magnetosphere, opens up the polar cap, allowing particles to precipitate in. So what happens? How can we validate this scenario? So we go from the one of the recent discoveries of 9 super flares from our sun. So the one of them is 775 AD event. So how do we know that? We look at the 3 rings. We look at the 3 rings. Sorry, this picture by some reason was 90-degree oriented. As the particle penetrate in, they strike the oxygen and nitrogen atoms. They create the carbon-14. So if the spectrum is hard enough, the carbon-14 is created in the first few meters above the ground, and carbon-14 O2 is being absorbed by trees. And that's how you get carbon-14 O2 in 3 rings. At the same time, beryllium-10 and chlorine-36 are found in ice cores in Greenland. So if we can have the data from 3 different markers, we will be able to reconstruct what's going on with the CMEs. So basically, this is the reconstruction of this is what's going on normally, with the CMEs from cycle to cycle. Okay, this is the number of particles per square centimeter from SCPs. This is the energy all the way to about like 1 giga electron volts. Unlike those, SCPs from super flares, you have those really, this big events, as I say, the super flare events from the current sun. And this is our reconstruction. It's 2022 of the paper published in Space in Science Advances, where we basically model the SCP events from flares from the current sun, from the young sun, and from the infant sun, to show that how the number of particles vary. That is important for the atmospheric model. So this is the map that shows, you can see those circles, the blue circles. This is the data of the 3 rings recovered for 775 AD events. You can see that this was an event of the planetary scale, so that you observe the 3 rings from Japan, at 35 degrees latitude to Yamal at 70 degrees, and you observe it in the United States, in Europe, in Russia, in Japan, everywhere, okay? So that creates us a good validation as the super flare. So why? So the 1 megaelectron proton can go to about 90 kilometers, 10 megaelectron proton goes to about 70, 100 megaelectron goes to about 30, and 1 gigaelectron goes into the troposphere. That's where the fun begins. When you have a sufficient number of protons at 1 gigaelectron volt and greater, you start seeing the very interesting chemistry. So we used this GGM model, global, the magnetospheric model, and coupled with the vacuum model, and that was developed by Dan Marsh. And so we're trying to, we calculate the vertical ionization profile and insert it into this model. This is what was going on when the XUV and the particles basically interact with N2CO2. This is N2O2 and a little bit methane water vapor. It creates different free radicals, CO, NO, and creates NOx's, and that creates eventually NOx's and OHX's, and destroys ozone. So we want to understand the impact of this big event on our civilization. So this is the work, and this figure shows that this is let's say the red one is NTO. The NTO goes up by 3 orders of magnitude. NTO, it's the very potent greenhouse gas, 300 times more potent than CO2. So therefore, it would have a very important contribution to the climate. So we found that the contribution is increase of the temperature by 1 Kelvin. And then, as you can see, this is the horizontal axis is the number of days. In about 500 days, it's slowly coming back. And the green one, it's the reduction of ozone. So the nice thing that, well, you're going to reduce ozone, looks like you're going to produce doomsday, but it's not. We're lucky that instead of this shield, you produce NO2, and NO2 is more efficient in catching the UVB emission. From that point of view, the surface UVB emission is not going to be affected that much. And then we use the same model for the early Earth. What it means that basically we're using the same model, but changing instead of O2, we use CO2. Okay, as the major greenhouse gas, and basically use the photochemical model to calculate the production of NO, and this is the basic reactions that NO and CH gives you HCN. The HCN is the major, the major precursor of amino acids and pre-biological molecules. This is basically the most important thought for molecules for biochemists. So we can produce that. We can produce formamide also pretty simply. Once you have HCN and you have water, you can produce formamide. This is another important thing. And we can produce formaldehyde. And we can produce, as I said, N2O. So the N2O is producing these models, by 1 per 1,000. So the N2O hopefully can create temperate conditions to keep water in the liquid phase. At the same time, if you have HCN, you can have the successful process of polymerization, forming major biological products of RNA and DNA. So, and ending my presentation soon with laboratory experiments, because you cannot rely on theoretical models unless you validate with experiments. So that's why as soon as this work was started, I was contacted by Japanese Kobayashi group that was doing the experiments in the dark room, for 30 years without having any implications for any kind of just GCM, just galactic cosmic rays. And we joined forces in order to start great collaboration. So this is the paper that was published about 2 months ago in the Origin of Life the journal, where we study, if you just use the, beam of protons on the mixture, gas mixture at one bar, and to CO2, methane and water vapor, and then study the production of amino acids, if any, as a function of initial amount of methane. This is the, in percentage-wise, from 0.5 to 10%, 20%, 30, 40, and 50%. So the blue circles represent the yield of, the glycine one of the simplest amino acids, as a function of the initial amount of methane. You can see that it goes up. What the red square is, it is the reproduction of Uri Miller experiment, which create the spark of light. But unlike his original experiments in 1953, that basically was done is the methane and ammonia and create a lot of amino acids. So here we replaced it with the N2CO2, a little bit of methane. You can see that if the amount of methane is less than 15%, you don't see any amino acids in his experiments. And even at that 15% or greater, so this ratio about 3 orders of magnitude. And it can be explained by the ways the proton interact with the atmospheres. I'm talking about a few hundred mega electron volts that create the multiple generation electrons that eventually, as they thermalize, create the dissociation products. And then we use this 1,000 part per million. That's how the tools are used. I mean, the Rocky 3D model. So this work was done several years ago. Wasn't published because we were looking for experimental confirmation for the N2O at the level of 1,000 parts per million. But we found that the mean temperature is 5.2 degrees Celsius if we assume 1,000 parts per million. So which can resolve the Feinstein-Sass paradox that still is a big question. And the last thing that I want to tell you about, that the whole this activity is now basically continues with the creation of a new lab at NASA Goddard. That my proposal was accepted to build the first lab in the United States, a so-called exoplanetary particle irradiation chemistry lab. It's EPIC, with number of chemists at the American University that has the diagnostic equipment. So we're also going to continue those experiments that we started with Kobayashi, and the Kobayashi, of course, the integral part of our lab. We're going to study the simple molecules, not just amino acids. We want to go back to the basics and understand the rise of simple molecules and how these simple molecules from experiments can inform us about the future JWST and habitable world observations. Might be that the models can give you so much, but they should be validated by experiments. So this is the first experiments that will be this is the proton beam penetrating the chamber. So the blue and red is the N2O2. So the question by itself, that how the N2O2 rich atmosphere responds to those particles during big events, during solar flares, is the question. Yeah, so therefore we would study the basic ion chemistry, that is responsible for the for the atmospheric stratification and that atmospheric drag that was discussed earlier. So what's next? Next, to apply the whole flotilla of open models, like models of the Community Coordinated Modeling Center. You see how many of them were developed. This is the models that described our sun. This is the model that described the magnetospheric response of of Earth, to the solar events. This is the models that describe mesospheric, all the way mesospheric, and this is the models that describe, and I added here, Wacom X, that one that wasn't there before. It's just a new addition to the old tools. So we have those beautiful tools that have been validated. So it is years of work. It's the tens of millions of dollars spent by NASA headquarters to fund this fund. And their work really good. That's the best we have. But the only thing that, of course, the range input parameters are pretty limited. So therefore, we need to work on expanding those input parameters in order to study those unusual exotic environments of exoplanets, in order to understand what's going on and how we can model, apply those tools. And another tool is so-called Exoplanet Modeling and Analysis Center, so-called EMAC. This is the part of the SEEC, Solar Exoplanetary Environment Collaboration, that is basically is the kind of like a prototype of the CCMC, but is built for understanding exoplanetary environmental parameters. So, and so therefore, this is the what's next. Next is the observations from JWST, and basically for calculating the transit depth spectra and trying to find conditions like N2O. That's one of the strongest absorber, and NO and NO2. And thank you for your attention. And again, we can only do it together.
Thank you so much. We do have time for some questions. Here. Over here, and then I'll come back.
Thank you for the talk. I have a couple of questions. My first question is about, you have modeled the response of solar energetic particle with the three suns, and you have considered the mechanism as a shock, CME shock. According to my limited knowledge, there are particularly three mechanisms for the shock acceleration, which is drift, then the shock, diffusive shock acceleration, and the response of that drift as well as shocks are different for the quasi-perpendicular as well as quasi-parallel shock. So, in your model, which mechanism you have considered as dominant?
Well, yeah, that's a good question. It depends. So the it depends on the energy of the CME. So the stronger the CME, the stronger is turbulence, right? The strongest turbulence, the more important is perpendicular diffusion. So basically, our model takes into account parallel and perpendicular diffusion, both of them, for different because we calculated the the SAP acceleration from CME speed starting from, as far as I remember, from 2,000 kilometers per second all the way to 5,000 kilometers per second.
My second question is for the magnet radiation belts of the ice giant planet, because if you are going to, if we are able to probe the mechanism for that radiation belt, then we can relate our theory to exoplanet also. So there is one mysterious question in that planet. There is, the radiation belts contain 1 MeV ions particle, and for that we required some sort of low energy plasma source that we have in Earth as well as Jupiter, but where we we have not yet observed anything in Uranus and Neptune. The way our Voyager 2 data gives us, there is some visual modes waves are also there in a magnetosphere of these planets, which are able to accelerate this particle. So is you are you planning any mission or any observation mission for these ice giant planet radiation belt mysteries?
Yeah, you're asking a wonderful question. That means that we need to look for the yeah, radio emission, the coherent radio emission that forms due to the interaction of the magnetic field dragged by the solar wind or stellar wind with magnetosphere of an exoplanet, that due to the reconnection create the precipitation of particles, right? And then you can see the gyrosynchrotron emission in that field. So that's one effect. The second effect is just direct, formation, let's say, H3 plus or other, depending on the planet, or O. N emission, like we see green corona or red corona, aurora from the Earth. By the way, that answer to your question, just about 3 days ago, the paper was published in Nature Astronomy, the detection of the H3 plus emission of the infrared aurora from Uranus. So yeah, this is the exciting work, and we're discussing, by the way, this as our activity point in our exoplanetary working group.
Excellent. We have 2 more questions queued up.
Nice talk. I have 3 questions. I'll go one at a time. Okay, nice. So I'll start with the first question. Then I have created a model where you can interact CMEs with planetary magnetosphere. So other than the UV flux that's going to tell you that the sun, the star has emitted a flare or a CME, do you expect, I mean, what kind of observational features you expect from the planet side? You said that you can expect the recent paper, you talk about the recent paper. Other than that, is there anything that I can look in my model?
Okay. So basically the one effect, well, depending on, so you see that the impact is from the side of precipitating electrons. Another effect is from accompanying protons, as I was saying, that if the superflare is strong enough, then you're going to have the impact of protons and some excitation of some emission. But the simple thing is, of course, is the radio emission, the coming from the ionosphere. Yeah. So, and this emission should be for a rocky planet at around about 10 megahertz. So it's pretty close to the ionospheric cutoff. But for like in mini Neptunes or giant planets, it can be between 30 to 70 megahertz. So which can be observed by low far and low frequency observatories. Yeah, so
That's
that's
nice.
the best bet.
I'll merge the first and second question. I mean, second and third question now.
Please.
Might be later. We can talk later. Absolutely, I will be happy to answer your questions.
Hi, so this question comes from my background in astrophysics. So have you compared or considered comparing the expected energy distribution from such a solar flare with what might happen if an AGN or active galactic nuclei were pointed our way instead?
You're asking a great question. This is the project that I started with the University of Rome, Tor Vergata. So, and I didn't even mention because it's only 30-minute talk. So the point is that we need to start with the galactic habitable zone or galactic habitable phase. Again, I'm not going to use zone. So meaning that when early on, at the early phases of galactic evolution, at the level of AGN, when the emission from the galactic center is so high in terms of XUV emission, also, by the way, there is a UFO. Have you heard about UFOs from galactic? No, UFO means the ultra fast outflows. So those ultra-fast outflows propagating from the galactic center at 10,000 gans per second, they propagate out. And of course, they're going to squeeze the heliopause, the heliosphere, all the way to the distance of magnetosphere. So at early on in the first, might be a billion years in galactic evolution, those forces gonna be dominant with respect with respect to the stellar forces. That's the question that a new area of research that we recently started with them. And it is important in the early phases of evolution.
This is a question from Slack. So when we consider energetic particle penetration, have we considered Earth's magnetic field evolution?
This is another wonderful question. So the point is that as far as we know, the magnetic field was kicked in, pretty early on, looking at the paleomagnetic records, at least 3.5 billion years ago. So from that point of view, in all our models, we're assuming the best scenario. Best scenario means the strongest magnetic field, so the Earth can resist to all the forces. Actually speaking, from that point of view, we were trying to understand. We know that more and more we study the young solar analogs and the space weather around it. So more and more, I personally get a little bit discouraged that the Venus was probably never habitable, or if it was habitable, extremely short period of time, because it should lose atmosphere pretty quickly. And our Earth, according to the atmospheric escape models, and we're going to do more research on that, shows that even our Earth was supposed to lose an atmosphere pretty quickly, but it didn't do it. Why? Because of the moon. I didn't mention that because we know that paleomagnetic records show that the moon had a magnetic field. Recently, Jim Green published a paper in Science Advances where basically they study those paleomagnetic records and build magnetospheres of the early moon that lasted probably a few 100 million years. And imagine that the interaction of the magnetospheres of our Earth with the moon can create an extra protection. Might be the moon is another additional factor of habitability that kept it against, because all you have to do, go through the first crazy period of the stellar weather evolution, okay, when it was particularly strong. So if the atmosphere survives, everything goes on. Yes, please.
Excellent talk. I have a question with regards to your habitability of planets.
Mhm.
My question is, in the process, when you were explaining the concept of the work, you said that when CMEs occur, we have the release of oxygen escaping from the atmosphere.
Yes.
So my question is it oxygen that we're using as a criteria for definition of life, or are there other molecules that we use in the definition of life?
Excellent question. So thanks for asking. Yeah, that's one of the most important questions. So there is a big misunderstanding in the exoplanetary community. People are looking for oxygen as a signature of life. So the oxygen was created by photosynthesis in Earth's atmosphere over the last few 100 million years only. It's about 10% of the history of our planet, okay? And we don't even know why. We don't even know whether photosynthesis is a law or it's a freak of nature. That's another question. But what we know for sure, that we need nitrogen for life. That's for absolutely, that's what you need. And you need, of course, carbon dioxide, okay? Because we know that the first so-called boring billion methanogens, which is life for me, no less than life today, survived, and they lived, pretty happily. But then something happened, and photosynthesis occurred. But what I'm saying is nitrogen and carbon dioxide. We need to look not for signatures of life. First, we need to look for the signatures of nitrogen-rich and carbon dioxide-rich atmospheres. If we find that, we can go forward. We need to go in small steps. First, the presence of atmosphere, then the presence of the important ingredients like NO excess, because nitrogen cannot be directly observed. We need to observe it by its products. And the one way to do it by its products induced by the magnetic activity. So that's my answer.
Excellent. We have time for one more question.
So this not gonna be a scientific question. It's more like back to the question you say. So based on your numerous experience in the habitability, is it Earth a unique planet in your perspective? And do you think the Sun-Earth system is unique? And do you think we can find a habitable planet in the next 100 years?
Okay, great. So the answer to a question is like finding Vladimir, in Golden, in this hotel, at my age, and ask, is the Vladimir is a typical Earthling? No, he's not. He's absolutely unique. Yeah, I think that, but I was a common Earthling when I was 1 month old. Because I have undergone through the billions of trajectories of the evolution. That's where I am now. My blood pressure and cholesterol and my weight and a lot of parameters, global and local, are as the result of the interaction, right? So therefore, the Earth actually, when you ask the unique Earth at what age, right? When the Earth at early age, yeah, it was common Joe on the street. But Earth 4.6 billion years after, of course it is unique, because if you compare Earth now from Earth 500 million years ago, it's two different worlds. So therefore, it's different planets at different times.
Thank you so much. Let's thank our speaker, Vladimir, one more time.
Thank you.
So next up, we have Eric Wolf from the University of Colorado, who will be talking about applications of 3D climate system models toward understanding exoplanetary atmospheres. You got 15 minutes. I'll give you some time cards.
And do you have this is the clicker over?
This is it right here. Green for forward, red for back.
All right, awesome.
And verbal cues work too.
Okay, thank you. So thank you everybody for having me here today. So I am at CU Boulder up the road, but I actually have lived in Golden for about 15 years and about 20-minute walk from here. So this is very cool. So today we're talking about applications of 3D climate system models towards understanding exoplanetary atmospheres. All right, and as Vladimir mentioned, you can go to the NASA Exoplanet Archive and look. They update it about weekly. At the moment, there are 5,500 confirmed exoplanets with another about 7,000 test projected candidates. So in the last, decade and a half, what we suspected as always being the case, we weren't so naive to think that all these stars in the universe did not have planets. But now we have direct confirmation that these planets exist, and we're getting increasingly better observations of them. And it's really opened a whole new wide world of physics that we can study. And I've been mostly interested in habitable worlds. That is sort of the crowning achievement that we're hoping to find. And currently, under conservative estimates, there's maybe about 24 potentially habitable planets, terrestrial planets within the habitable zone we found, and 63 in a more optimistic range. Now, that seems a small number out of 5,500, but there's a strong detection bias towards finding very big planets, very close to the stars, hot Jupiters. So we expect in time these numbers to continue to grow. And I know James Webb is in the sky right now, which was not designed to look for exoplanets. It's being co-opted to do that. But the next large space observatory, the Habitable Worlds Observer, is actually, they're having a meeting this week to kind of kick that off, I believe, will be specifically focused on trying to find and characterize these type of planets. Now, so I'm a modeler, a climate modeler by trade, and it's been the weird world of exoplanets has really opened the door to all the different types of physics that can be studied. And these are, the details don't particularly matter. This is hydrogen simulations of a hydrogen-rich, tidally locked exoplanets with clouds and water vapor. And so I use climate models, 3D climate models used for climate change, and I use them for these more general problems of exoplanets, Earth through time habitability, and problems like that. So 3D climate models can allow us to explore theoretical exoplanetary atmospheres by coupling together all these many different processes. Now, any given process, a 3D climate model does not do the best job. So radiative transfer, for instance, which I've spent a lot of time on, a line-by-line code will be better than any band model, correlated K model you see in GCM. Likewise, the dynamical core, we tend to use coarser resolutions because they're expensive to run. If you run a coarse resolution GCM, that's not as good as a quarter degree to quarter degree model that you might run for a expensive climate change simulation. Likewise, with clouds and convection, a large eddy simulation on a small grid box is going to do much better than our subgrid scale parameterizations. But kind of the secret sauce with the GCMs is that all these processes are coupled together and interact together, and we can analyze these nonlinear effects, these complicated effects within the climate system. And then when we think about exoplanets, they're undergoing novel, sometimes extreme forcings, different gases in the atmosphere, different stars, different amounts of stellar energy. And then all these processes are coupled together, and we see how they interact to define a climate. So there are two schools of thought currently about how to develop an exoplanet GCM. The first is to start with a dynamical core and iteratively build outward, adding the physics only as needed. You see most hot Jupiter models tend to follow this path. The pros are you have full control over the model architecture. You have full control over what physics goes in the model. There's no Earth-centric quirks that are going in. The cons is this is a difficult and time-consuming and expensive way to build the model from scratch in the academic environment. You have the models like the NCAR model and the community-supported models have been developed over many decades by hundreds or more people, so it's hard to start from scratch by yourself. I have lived mostly in this second school of thought here, or I'll say exclusively, where you start with a nationally supported climate model, and then you can modify it to suit your needs. Use some pieces of physics you like, eliminate pieces of physics you don't. The pros are you can leverage a wealth of legacy code developed for Earth climate, and much of which can be repurposed, specifically if you limit your scope towards terrestrial type planets and don't go into hot Jupiter regimes. So it's easier to get started modeling, and these Earth-centric community-supported models are reasonably well suited for many habitable world scenarios where you're looking for water on the surface, things like that. So the cons are you have to adapt to the architecture of the parent model. The nationally supported models are typically focused on modern climate through RCP scenarios, so they have a lot of infrastructure geared towards that, which you have to sift through. There's Earth-centric physics routines that you have to be mindful of, constants that may remain hidden in the code, even though I think mostly they've all been pulled out as to compile time parameters. I use the NCAR model. I'll still go through and I'll see a random 9.81 or a 2, things like that, or a molecular weight of the atmosphere, 28.96 hidden in places and that haven't been caught. So things like that. And one of the cons, not really a con, but it's the radiative transfer almost always needs to be replaced because radiative transfer is very expensive. So the Earth-centric models have pared the radiation down to do Earth pre-industrial through the RCP scenario, Earth is very well, but if you start to get weird, you start to get a dense CO2 atmosphere like early Mars, or a Titan-like atmosphere with a whole bunch of methane, they start to break down. So physics implemented in GCMs, it does tend to be reasonably flexible, allowing for the simulation of terrestrial exoplanets, and then we can start changing things iteratively to do generic terrestrial exoplanets. So the first thing we would change, for instance, would be the boundary conditions, continents, oceans, glaciers, topography, etc. I mean, this is pretty straightforward into a boundary condition set. I'll say generally straightforward, but there are parts of it that can be extremely tedious. I don't know if anybody has looked at the CSM Paleo Toolkit. It's about 35 steps in binary files, and that is tedious. Likewise, in the Rocky 3D GCM, people have tried to change the river runoff directions, which itself is extremely tedious. The next thing, changing these bulk parameters, the planet, mass, radius, surface gravity, these tend to be fairly straightforward to do. Thank you. For parameter changes, atmospheric compositions, total pressure, greenhouse gases, condensable species. Again, this is typically requires the implementation of a new radiative transfer in order to be able to handle a bar of CO2 or 5% methane, which itself is a challenge, but mostly done for these exoplanet models. Also, sometimes you have to work on, I like to refer to the plumbing in the model to make sure that the species concentrations you're setting are getting to your radiation and the rest of the model appropriately. Like in my model, I just added another new gas that doesn't exist in CSM, so I added ethane to look at early Earth studies, and that doesn't exist, so I had to make my own plumbing, if you will. And then stellar input, total stellar flux, and the energy distribution. I say straightforward, particularly once these new radiative transfer codes are implemented, because they're designed to be able to flexibly change these things. Orbital properties, obliquity, rotation rate, eccentricity. Again, it's not terribly difficult, but one of the problems that we run into is that with the keeping of time, that the calendar system is tied to the timekeeping of the model, is tied to the output frequencies and options in the model. So you have to be careful when you are changing the rotation, or the orbital period and the rotation rate of the planet, of what it means to have a month or what it means to have a day in relation to your history file outputs. And then advanced properties, I say this is hit or miss, model dependent, whether you have aerosol layers or ocean heat transport or photochemistry. People have used Wacom for exoplanet studies. You can change out the chemistry in Mozart, but it's difficult to do to change the reaction networks. Some model, CSM also has Karma, which you can turn on and use. Rocky 3D has ocean heat transport that works really well. So it's, specific models have different things that you can leverage for these more advanced properties. All right, so today this is an incomplete list of GCMs that are to use for exoplanet type studies. The ones, I'll kind of gloss through the list here for time, but the ones that I use mostly are, so at the bottom, the NCAR CESM with ExoCam, which is a patch that I've developed that's on GitHub that I've developed starting from graduate school all the way through till now. And I also work with the Rocky 3D model, mainly using the radiative transfer code. A couple of the other ones, the LMD model, they're arguably the leading group out of France. They've been working with the exoplanets for quite a long time. So 3D climate models have been used for a wide variety of terrestrial exoplanet studies, which I don't have time to get into all the details in the short talk, but things such as defining the habitable zone, which Vladimir discussed, the inner edge where you have moist and runaway greenhouse properties, you get too hot, the outer edge where CO2 starts to condense, and you can't warm the planet anymore, or in and out of snowball Earths. These tidally locked M-dwarf planets have been a focus of study. They have very different dynamics. There are, as Vlad can tell you, there are issues and questions about whether these planets actually have atmospheres due to the strong activity of the sun. And in a way, as my close colleague and friend Ravi Kaparappu likes to put it, we are looking under the lamppost for our keys as we are studying these atmospheres, because they're what we can see and what we can observe at the moment. It doesn't necessarily mean they are the best candidates out there. And then next is flavors of exo-Earth. So this is what the Habitable Worlds Observer is really going to be looking for, not M-dwarf planets, but Earth-like planets around G and K dwarfs. K dwarfs are a little bit cooler than G dwarfs. So you have the stellar spectra and the stellar constant, planetary properties, greenhouse gases, water inventory, rotation rate, orbital stuff. Just there's a lot of parameters you can think about. Not an infinite, but if you start putting that in a data cube, it becomes just absolutely unwieldy to think about. And then observability. So ultimately, we want to kind of get out of our modeling sandbox into how we can connect. And I enjoy the modeling sandbox. It's really fun. But we want to be able to connect more directly to observability, transmission spectra, reflection spectra with HWO, thermal emission phase curves. Clouds and hazes have been shown to have an outsized effect on the observability. And so where is the field going next from the 3D climate modeling perspective? So as I said, there's a strong desire to start connecting with observations. So we are getting good observations better observations, I should say, of the larger planets, mini Neptunes and hot Jupiters. There's more direct connection with those to observations now. In the realm of terrestrial planets, we're still kind of waiting, if you will, for better observations. And one thing that's been asked of me as a 3D climate modeler is, could we put together a large database of models that could be used as a reference, similar like the BT? I'm almost done. This is my last slide. The BT settle model of grid of stellar models. If we can put something similar together with GCMs. But the problem is there's such a massive parameter space to explore, and the models are prohibitively expensive to run. So one thing that colleagues of mine have been working on are sparse gridding solutions, where you can take a huge parameter space, sparse grid, and try to interpolate between those points to get something useful out of it, not just for retrieval, to inform retrievals and current observations, but also in the target selection and thinking of future missions as the HWO is currently getting set up to be designed. So thank you for inviting me and listening to my talk. I'd be happy to answer questions.
Thank you so much. We're going to skip questions for right now and come back after the next talk.
Sounds good.
So please stick around for that. Hold those questions and have them ready. Next is Mayun Lin, who will be speaking about molecular ion outflow and implications for habitability. Ready to go? Let's see. Make sure you got that. This forward and reverse.
Can I try it?
Audibly cue. Yeah.
Oh, great.
Excellent.
Hi, good morning. My name is Mayun Ling. I'm currently a postdoc in California, Berkeley. Today I'm going to talk about molecular ion outflow. This work has been mostly done in my PhD work in the University of Illinois. And I would like to thank my co-authors, PhD advisor Raluca Elia, and the model collaborator Alex Glosser from NASA Goddard. This project has been supported by NASA, Air Force of Scientific Research, and of course, and NSF. Too many support, and this funding support make my PhD fruitful, but also busier. And before I started, I want to say two things. First, I want to thank the staff and Carrie, Dawn, Cindy, and Kate to organize such a symposium. And second, I met this title like 2.5 months ago, and I realized I should expand this title. It's not only implication to habitability, it was implication to everything. Sun, Earth, or like climate, or even space weather. Today I'm going to propose just one thing, and potential energization mechanisms that connect Earth atmosphere to ionosphere, magnetosphere, and at the same time related to the solar physics input. So what is ion outflow? Ions with sufficient energy can transport outward to outer space.
And there are two main pathways. The first one is in the low and mid latitude ionosphere, which the magnetic field is dipolar and closed. This is called trapped cold ions with energy of eV. The second path is in the open field lines in the high latitude ionosphere. And based on their energies, we can refer to this high latitude ion outflow as cold supersonic ion outflow with EV, or energetic ion outflow with KeV. So for the mid and low latitude ion outflow, it can compose with hydrogen ions and helium ions. And in the high latitude ion outflow, it can compose of hydrogen, helium, but also heavier species such as oxygen, nitrogen. And during the space weather events, we found molecular species, including NO+, N2+, and O2+, in the magnetosphere ionosphere system. So my next question is, can molecular ions stay in the ionosphere? For this question, I reviewed the past observation data on molecular ions in the past 60 years. And I found that we can have molecular ions everywhere in the space, from hundreds of kilometers altitude to tens of Earth radius, cover different solar cycles. And if I look further into the observational record, they tell us one thing. During the quiet time condition, you literally found no molecular ions above 1,000 kilometers altitude. But once you have space weather events, any perturbation or like any DST, geomagnetic activity, you start to have huge amount of molecular ions appear in the Earth magnetosphere ionosphere system. So that telling us abundance of molecular ions is very sensitive to the geomagnetic activity. And I have to say one thing. I found out in the past 10 years, we have a lot of observational records on the molecular ions. And this is because we have improved technology of the IMAX spectrometer on board the spacecraft mission. That's why we can have more and more observation of molecular ions, which means I believe the open science and AI technology, when discussing this meeting, will open the more discussion on what happens in the our space system. But why do we study molecular ions? Because NO+, N2+, O2+, they are the major component of ionosphere F and E layer. So their abundances are strongly connected with what happens in the thermosphere, ionosphere, and neutral atmosphere. And in addition, the huge difference of molecular ions during quiet time and storm time give us an idea about the energization mechanisms that can suddenly energize those ions that which mass is double than oxygen ions, can transport outward to the magnetosphere in just a few minutes. So if we understand what happens of these energization mechanisms, we will know what happens during the extreme conditions, and that will give us an idea about atmospheric evolution during the exoplanet. So this is gonna be my very theoretical slide. I'm gonna be very quickly. The potential energization mechanism I propose is called the energization of wave-particle interactions. Okay, the basic idea is that the ion gyro frequency is resonant, can be resonant with a portion of the wave perturbation in the ionosphere. And when they are resonant, the part of the electric field perturbation can increase the perpendicular velocity of the ions. And because ion is transported along with magnetic field lines, so part of the perpendicular velocity will be transferred to the parallel velocity. That's why if you see, if you draw a velocity distribution of the ions through the wave-particle interaction energization, they will become a pancake shape because the parallel velocity will increase along with the perpendicular velocity. And this energization mechanism is mass sensitive, which means for the molecular species, because their mass is double, they will be much more sensitive to get more energies from wave perturbation than oxygen and hydrogen and nitrogen ions. Unfortunately, the current instrument technology cannot resolve the wave spectrum in the ionosphere, so we don't know what happened. And the only thing we know is the oxygen ion spectrum. So I kind of designed a simulation that can that based on the fact of the oxygen ions energization through the wave particle interaction. I include those and transfer that part to the molecular species and put it in my models. So this model is a hybrid model, transport model, transport equation below 1,000 kilometers altitude, and above 1,000 kilometers altitude, I give them a wave energization. And let's see what happens. So here is the left-hand side is the velocity distribution function. The right-hand side is the ion density profile from 200 kilometers altitude to 8,000 kilometers altitude during no wave condition. And this is N2 plus. It's suddenly the density just go down very quickly. And same for NO plus and O2 plus. So we kind of know that during a no wave condition, there's no molecular ions can be possible transported outward to the magnetosphere. But once we give very little nominal wave energy, the picture start to change. You start to have molecular ions appears in 2,000 kilometers altitude, but those ions are not energetic enough to transport to 4,000 kilometers altitude. And same for NO plus and O2 plus. And the best part is we kind of know then we start to have a molecular ion outflow, but not outflow. So we will have some energetic molecular ions in the 2,000 kilometers altitude, but they don't have sufficient energy, so they will go down eventually. But just increase the wave energy by a factor of 3, the whole picture changes again. You have sufficient energy, like suddenly the molecular ions have sufficient energy to transport to 4,000 kilometers altitude and then never come back. And just by increase wave energy by a factor of 3. And we are doing modeling, so we can just input like a crazy number we have. If we increase by 3,000 factors, is that you suddenly depleted all of the molecular ions from ionosphere to the magnetosphere. Everything, all of the heavy species, they will be energized suddenly just with the wave energization mechanisms. So this is going to my summary. During the early Earth condition, our magnetic field probably is not stronger. It would be like weaker. And this energization mechanism is tightly connected with the value of the magnetic field. So if the Earth's magnetic field is only 30% of whatever we have right now, you will suddenly have a lot of molecular ions transported to the high altitude. So I propose this energization mechanism as a link to understand the habitability. What happens of the atmospheric evolution, especially for these heavier species, during a completely different stories? Do we have more heavier species? Can that be a restriction? And we can use this as a clue to understand what happened in the Earth atmosphere. The second, this link with the atmospheric chemistries. So the neutral atmosphere and the ion composition gonna change the whole story, and we need to better understand what happens of the ions during the exoplanet conditions. And this is not only restricted to the molecular ion species, we can have that in the metallic ions, and I'm going to do that in my next 2 years, and hopefully I can give you a better answers after 2 years. Thank you so much.
Thanks to both of our speakers for really interesting talks. We have time to take questions now for both Eric and Mayun. I'll walk around with the mic. Vlad, over here.
Yeah, thanks for nice talk. Just one question. So the point is that have you taken into account XUV flux? Because if the XUV flux is high, then the XUV flux will dissociate those molecules and create a lot of M plus and O plus. So I was just wondering that might be you use the low XUV fluxes when those molecular ions still survive. Because the higher the XUV flux, the greater the dissociation rate, photodissociation rate.
Oh yeah, so this one's only during solar maximum condition. This one, so we do consider that molecular and species chemistry as well.
Yeah, and the second question about this the electric field induced by waves. So how do you have any ways to parameterize the wave density, energy density in waves versus magnetic activity? How to? Because I don't understand how it works.
Well, this is a very big challenge right now in the magnetosphere community because there's not a lot of observational data we have. And I propose this as like, in addition to detect the wave spectrum, maybe we should detect molecular species because they can give us an idea about the wave.
Thanks to the two speakers. I have a question for Eric, actually. Yeah. So in the final slide, you mentioned something about having sparse parameter space estimation across multiple models. So is this something like a surrogate model for all the models that are present, or like what? How do you go about doing this? Do you have some ideas? Yeah.
So I wish my colleague. Oh, thanks. So there are a few ideas. It's not my own novel idea. One of my colleagues with Rocky 3D is doing what's called a Latin hypercube, where she has 10 different dimensions, and the grid is in a certain way where there's one value is chosen for each of the 10 dimensions, and it's been still difficult to try to integrate that sparse of a grid. And I wish my other colleague Jacob Hockmeister was here. He just submitted a paper where we were looking. He's using actually a technique from geospatial statistics informed from actually mining, where in the problem for mining, if you're looking for gold or a valuable mineral, you have very expensive drill cores that go into very certain locations, and using those techniques to interpolate our GCM models. Now, we thought about, of course, everybody's using AI and machine learning, but in those problems, you need a lot of sampling to fill in the gaps where we have the problem of having very sparse sampling. So, there's a few. Those are a couple of the ideas out. I like my colleague Jacob's statistics from the mining example. So that paper is under review right now. So it's coming out soon. So thank you. Good question.
Thanks. I'm going to suggest you guys might want to share the podium mic, and that way I can run this one.
My question is for me. Have you explored the role of that Whistler jets in the wave particle interaction of these molecular ions, particularly Whistler mode jets? Whistler mode waves are a major candidate in the magnetosphere regarding this wave particle interaction. So, have any idea of observational studies of these wave particle interactions with the Whistler waves?
Whistler wave. Yeah, there's a lot of debate on the source of this low frequency wave in the ionosphere. And people will talk about Whistler wave, Emic wave. There's so many waves in the magnetosphere. But as far as I know, none of them can explain what we observe in the ionosphere. So this is still an open question, and I really wish some magnetosphere people can jump into this and tell us what happened.
This question is from Slack, and it's for Eric. How do you do validation for these models? And just a thought, Venus was supposed to be habitable in the past. So is it possible to validate the models by running its evolution and compare it with current?
So thank you. That's a very good question. And For one of the ways, as was brought up, that we try to validate the models is by comparing with the one planet we know the best, which is Earth, and then also Earth through time. And that's how I got my start into this field of habitability and exoplanets. So I was really thinking about the Archean Earth, which is a very alien world compared to the modern Earth. So, and now also thinking about Venus and Mars as well are two other planets that we can run validations of both planets through time to see how our models do and compare with the geologic records and whatnot. Another big thing that we do as a community, we're thinking about when we're thinking about exoplanets where we don't have a ground truth we can validate with for a faraway exoplanet, is doing model intercomparisons have grown in our field where we've taken, I showed a list of models, we've taken four of the major models and run them for these same stock exoplanet cases, and we find we get kind of, within the wide margin of error of our exoplanets, we kind of get the same results from all the models. Not close enough when you're thinking like CMIP, but when you're within 5K for an exoplanet, that's pretty close and pretty good and gives us confidence that the models are doing something, either they're all wrong or they're all, converging to a agreeable solution.
So both were really excellent talks. And I love the parameterization space of the second talk, your talk. And so I have a question for you based on that, Eric, and that is, so the Slack question was sort of validation of models, right? With the world of exoplanet and even our terrestrial planet sort of opening up in greater detail for us in terms of observations and data, I mean, are there any models or thoughts of thinking of our planet Earth as an exoplanet from we can now recreate that, right? And try to validate what we are going to observe or observing. What kind of truth is there?
Yeah, that's definitely something that the field is doing from many angles of thinking Earth as an exoplanet through time, taking Earth observations of things like ocean glint and how that might be seen from afar. So that is definitely a point of emphasis, as well as there's been a recent successful conference series called Exoplanets in Our Backyard. And the whole premise of that is to use solar system objects as our templates to work from there outwards, because even obviously Earth, but even planets or moons, I should say, like Titan, which are very alien, we have worlds better data from a place like Titan, or the comparison of mini Neptune planets, which are common to the Uranus and Neptune. So there's a big emphasis in the exoplanet field to try to collaborate with and leverage all the solar system data we have, but thinking about it in that exoplanetary context. So that's a very good point. It's a point of emphasis.
So you can put some of these links on the Slack.
Okay, sure. I will. Yeah.
Eric,
one here.
Yeah, question, Eric, about habitable worlds is going to come along and perhaps characterize the atmospheres of a lot of the planets. But with your models, you've got the ability to really span the parameter space and see what things we're really sensitive to if we want to have a kind of nice, stable, life-evolving planet. Habitable worlds will see things at one season all the time. How sensitive are stability parameters that might enable life to things like orbital effects? That would be something that you'd be able to explore.
It is, and I think a lot of sort of I'll call them low-hanging fruit type problems, or people have taken the GCMs and they vary eccentricity or obliquity or standard parameters like that, or the stellar flux have been done. So we have libraries of those. So for orbital properties, as you mentioned, planets tend to be pretty durable to wider eccentricities or different obliquities as far as being generically habitable. That the stellar flux tends to, the importance of it tends to average out over the course of a highly eccentric orbit, if you will, where the sun kind of rules all, right? So the stellar spectrum, and in combination with the amount of flux received by the planet, are strong arbiters of how climate evolves. And in time, like as Vlad said, that it's not a static zone. There's the age of the star and the star brightening through time, and thinking of Venus when the sun was less bright in the distant past. So orbital variation in the orbits, not so much sensitive, but the variation in the sun and how bright it is in time, in the spectrum as well. When these M dwarf planets are very much, their peak is at 1 micron instead of at where the sun is. So that changes climate dramatically because it pushes the sun's energy, the star's energy, into where there's a lot of water vapor, CO2, and methane bands. So kind of hand waving around the question, but yeah, there's just so many parameters to think about that, but still the sun kind of rules all.
I'm going to exercise chair's prerogative and ask Mayun a question, which is, I was really intrigued by your analysis of how waves affect different species differently, especially because we'll probably see these jets with punch. We know we'll see at least some high altitude jets. Have you thought at all about the morphology of the different types of jets and how we might be able to distinguish them?
Well, we did some simulation about that, about like what is the lifetime of this molecular and outflow in the space. So we did some research on that. It's a very time sensitive. It's also it's just a very limited region. So this molecular outflow will be very possibly exist when you have active wave regions, which in our understanding so far is near the cusp region or like near the auroral region. So that will be the only region, 2 regions in the space that will have molecular and outflow. And this is not going to be a large scale structure plasma. It's going to be mesoscale. Their latitude will only be 5 to 10 degree latitude, depends on how energized they are. So I agree, and I think this will be a possible direction to understand those jets and like a mesoscale structure plasma from ionosphere to the magnetosphere. And but we need the input from the thermosphere, atmosphere, or like ionosphere to tell us how many ions are from the lower altitude, and that will tell us a more idea about it.
I hope you'll come to Punch 5 and help us brainstorm.
Huh?
Punch 5, meeting in June.
Oh,
We'll talk afterward.
okay.
Thank you.
Both great talks. I have a follow-up question. What can we learn about looking at ion escape across the planets in our own solar system that maybe you can apply to understanding what's going on at Earth?
Yeah. So this model that I developed, this model is not only limited to Earth. They only have they also have Saturn version, Jupiter version, and we are thinking of to add an exoplanetary version. The physics is very similar, and just the neutral atmosphere is different. Your ions are different, and your chemistry are different. So I think we start with the Earth. And I never thought, I heard about exoplanetary in 2018, so I'm very new to exoplanetary field. We start with the Earth, and based on our experience on Earth, we applied that to ion outflow in different planets. And that tells us a better idea because we have some standard to validate our results and to validate our science. So I think there's a lot of things in ion outflow to do in different planets, and I'm very open to any discussion on that.
All right, so very last comment from Vlad, and then we'll close out this session.
Yeah. So Dan, the answer to your question is that the major ion escape rate depends on the exabase temperature. So, and the exabase temperature by itself depends on the chemistry and those molecules that cool the exosphere. Specifically, it's either CO2 or NO. So if you have a nitrogen-rich atmosphere, NO kicks in and may, depending on how much you have, can decrease it, and that will strongly regulate the ion escape. So that's one of the major parameter. No. Of course, no. Right. Yeah. But it's so our simulations. We use this model for exoplanets, and we tried for distant exobase. So you increase the exobase temperature by a factor of 2. You increase the ion escape rate by a factor of 8. So that's why it's very sensitive.
Thank you. All right, let's thank Eric and Mayun again for very stimulating talks. And I don't want to stifle the discussion, so let's carry on during the break, and we'll reconvene at 10:35. Is that right? Or 10:30? 10:30.
Hello. Is this? I think we are going to get started with our next session. I think we've been busy communicating with each other. I don't know if someone can go out and bring in if there are other, team members out there. Our next talk, continuing in the theme of exoplanetary habitability, is going to be given by Shudan-san and from University of Hawaii. The topic is the missing stellar CME conundrum: lessons from the sun. I like the title. Thank you.
Use this. All right. Okay, the green button is the advance, I suppose. Okay. Okay. All right.
I think we have to. Is this on?
Hello? No. On. Okay. Hello? Okay. All right. Good morning, and thanks for the organizing committee for to invite me to be here. And it's a really interesting and exciting experience here. So I am going to switch gears a little bit from directly looking at the exoplanets to looking at the stars. So Vladimir already mentioned that to characterize the habitability of exoplanets, there are different aspects you need to look at. And the impact of the stars, in particular their energetic events like flares and CMEs, is one of the important aspects. And I am going to focus on just that. So my background is in solar astronomy, and recently I ventured into the dark side, the stellar, astrophysics, and I think that's where the connection to exoplanet lies, and I think that is where the interdisciplinary approach would help us. All right. So this is the outline of my talk. First, I will briefly describe what I meant by missing stellar CME conundrum. And then I will talk about some of the observations from the sun, in particular, the so-called failed eruptions, and what can we learn from those failed eruptions. And then I will use what we learned from the sun, from the failed eruptions, to help us explain how to address the missing stellar CME conundrum, and that is the suppression of the torus instability, which is a plasma instability that drives coronal mass ejections. And finally, I will talk about what we are going to do next. So on the right-hand side, you can see that is one of the earliest image of the CMEs. It's called Granddaddy CME, nicknamed, captured by HAO. I believe this is a H-alpha image. But you can see that the coronal mass ejections, which is the fast ejections of the plasma in the stellar atmosphere, usually takes the shape of a slingy here, right? And you can see these twisted structure, which outlines the twisted magnetic field lines. Okay, so first, some background on stellar eruptions. Okay, stellar eruptions, including CME flares, they are fundamentally driven by the magnetic field. So based on what we know about the sun, we think most of them follows this particular magnetic structure. Okay, I don't have a pointer, but let me just walk you through this. Okay. So in this cartoon, this is the photosphere where it's very dense, and everything above it is the stellar corona, which is very tenuous. And because the density is relatively low, most of the dynamics is driven by the magnetic field, which is shown here as these curves. Okay, so these magnetic fields are rooted in this photosphere, and what you'll see is these circles, which corresponds to the twisted magnetic field lines that we call magnetic flux ropes. Okay. So these twisted magnetic field line would actually contain lots of energy, okay? And when there is too much energy, it will become unstable. And the whole top part of this structure, the magnetic flux rope, will erupt upward, and that is the body of the CME. So the magnetic structure would carry the plasma with it. And when it does so, what happens is that down here, where the magnetic field is tethered to the photosphere, they would come together to the center part, and that's where the magnetic reconnection would occur. And the magnetic reconnection would energize particles such that a large fraction would be ejected downward, and these energetic particles would hit the dense lower layers to heat these lower layers. Okay. So when the lower layer is heated, it would emit brightly, and that's where we get the flares. Okay, so upward CME, downward in the lower atmosphere, and the remaining coronal loops, post-reconnection loops, you get the flares. Okay, so this is the basics of the stellar or solar eruptions. So in some sense, flares and CME are two aspects of the same fundamental physical processes. They are just different manifestation of the release of magnetic energy. Okay. Of course, there's also a population of fast particles that we know as energetic particles. That's also could be geoeffective or affect the habitability of exoplanets. Now, they are the same process, but one can indeed occur without the other, and that's what we found on the sun. And they will have different consequences to the exoplanet habitability. And that's why I want to make a differentiation between flares and CMEs upfront. So we have plenty of observations in the white light, and this is a coronagraph when the sun is blocked in the middle, and then we see the eruption of the coronal plasma, and as you can see pretty clearly the twisted structure in the center. Okay. Now, this is a SDO AIA image in UV. You see the active region here, and then you see the ejection of the plasma. And we're interested in these eruptive events because they tell us a lot about the plasma physics. They tell us a lot about the stellar astrophysics. For example, in this particular case, this eruption ejects lots of plasma, but some of it actually falls back down, and they actually impact, they re-enter and impact the lower atmosphere. And you see brightening there. And that is a pretty good visual demonstration of the accretion process, for example. And of course, the outflow of the plasma from CMEs would carry some amount of the angular momentum, right? So that tells you, that gives you one mechanism of loss of angular momentum, right? And to our main topic, exoplanet habitability. Okay, so flares would give you a large amount UV and X-ray emission, right? And it will also possibly give you a high energy particle flux from the CME. So SEP, I mean. So this is one way to affect the habitability. But of course, the majority of the impact, that way we know, is coming from the CME, the bulk of the plasma, magnetized plasma that's interacting with the magnetosphere of exoplanets. And that is the main, one of the main processes that is driving atmospheric loss. So CME is the main driver, one of the main drivers. Okay. Now, we now know from the astrophysical surveys that flares happen frequently on other magnetically active stars. Most of them are these late type cool stars like our sun, or cooler than our sun. So on the right-hand side are two Kepler light curves. And on top of these large modulation from the star spots, you see these sharp peaks. Okay. And that is the superflares, so-called superflares. They are super because if you look at the bulk energy, bolometric energy, they are usually about 100 to 10,000 times more energetic than the solar flares. Okay, as you can see, in the blown up, the light curve, the peak brightness is a few percent of the stellar flux. Whereas if you look at our sun, I think Greg showed this plot early, and this is on the top is the X-ray light curve of one of the most energetic flares we've ever observed. So in the X-ray, we see a very clear, impulsive peak. That's because the solar X-ray background is relatively weak. However, if you look at the TSI, total solar irradiance variation, even if you do overlapping of multiple events, the most you can get here is about 20 parts per million. Okay, so the effect of large flares on bolometric emission of the sun is quite tiny. And if you compare to the flares in the previous plot, you can see that's 8% in the bottom. Okay, so there is quite a few order of magnitude difference. So the flares on other cool stars are really, really energetic compared to our sun. Okay. And our understanding currently is that they happen, the mechanism of those super flares is most likely the same as on our sun, which is driven by the magnetic field. And we have many evidence to support that. Now, CME, actually, Vladimir showed this similar plot, but for cool stars, the detection of CME is somewhat difficult. That is because on our sun, when we see CMEs, we see a beautiful movies, right? We see white light emission. We see material being ejected. Whereas on other stars, we don't have resolved images. So there are different ways to detect it. Most of them relies on spectra. Okay. For example, this is the example Vladimir showed, where you see the absorption, okay, of the H-alpha emission that is interpreted as the cool material from CME blocking the stellar light. Right. So that is one way to detect it. Now, the interesting thing here is that for the flares in the survey, we've seen thousands of super flares. Okay. However, for CMEs, they are relatively rare. Okay, so far we've only seen a few tens of candidates from various techniques. Okay, so that is somewhat interesting because this is not consistent with what we see on the sun. And despite recent dedicated surveys of particular active stars, nearby active stars, we still haven't found many. Okay. So I think that is the missing stellar CME conundrum, because if you look at our sun, the more energetic a flare is, the more likely that flare is associated with the CME. And this is a histogram. Okay, on the x-axis is the flare energy, and on the y-axis is the CME association rate. And you can see a clear increase of the association rate. And for the most energetic solar flares, almost all of them are associated with CMEs. Now, if you extrapolate it by another 2 orders of magnitude, you would imagine that on the cool stars, all of the superflares will be associated with CMEs. So in that case, if we find 1,000 superflares, we should detect 1,000 CMEs, right? Even if our detection is somewhat biased because of the difficulty of detection, we should still see quite a bit more than the 40 or so that we have found. So that is inconsistent, basically, with our understanding of the CME production on the sun, and that's what I call it a missing stellar CME conundrum. And it is quite easy to see where the problem is, if you cannot find these missing CMEs in terms of the exoplanet habitability, right? Because all of our understanding of the exoplanet habitability depends, or correlates with our understanding of the sun. So if you don't have enough CMEs, where you have a lot of flares, the way to drive atmospheric loss will mainly have to come from the UV radiation instead of the interaction of the CME magnetic fields with the exoplanet magnetosphere, right? So the way we understand the atmospheric loss will have to be reevaluated. Now, there are different ways to understand why that is possible, why that is happening, right? So we think that it is unlikely that it's observational bias because people have already started to do these dedicated campaigns, but still we haven't seen any. It is also unlikely that there's some novel physics at play because all of the statistics of the flares point to the same physics, the magnetic energy release of the flares and CMEs. So what we think is possible is that for other cool stars with a more stronger magnetic field, there is a different magnetic field environment compared to our sun. And we say this is that the reason we say that is because if you look at our sun, amongst the population of all the cool stars with magnetic fields, we found the sun to be pretty inactive. Okay, so on the right-hand side, I'm showing you a plot in the x-axis is the so-called Rossby number, which basically characterize the periods of a star. So towards the left, the period is shorter. That means the stars are rotating faster. And we think that a fast rotator will have a stronger dynamo. So it should have a stronger magnetic field, right? And on the y-axis is the X-ray luminosity, which is a good characterization of the magnetic field. So the brighter the X-ray is, the stronger the magnetic field. So stars, magnetic fields on the cool stars will follow this interesting power law, right? And at a certain point, it will saturate. That means the magnetic field will become stronger and stronger as the stars rotates faster and faster, then it saturates, right? So we have all these samples of cool stars, and lo and behold, our sun is at the lower right corner. It rotates pretty slowly, and the magnetic field is pretty weaker. So the sun is not a very typical, cool star. The magnetic field is relatively weak. So that's why we have some reason to believe that our sun is quite atypical compared to other cool stars. And that is the magnetic field on other cool stars can be very different from the sun. So I will expand on that for the remainder of my talk. Okay, now let's take a look at the theories of solar CMEs. There are many different magnetic field theories or models to explain the CMEs. And these three cartoons are the basic, three major classes of models. Okay, so I'm not going into the details, but what is in common is that in order for the CME, okay, the body in the center to erupt, not only does it have to go through reconnection to get it severed from the tethering of the magnetic field, it will also have to go through all the layers of the magnetic field that is above it, the large-scale magnetic field. Okay, so there is a competition at play, right? So there is, on the one hand, you have a magnetic flux rope that is expanding and trying to erupt. And on the other hand, there is a background large-scale magnetic field that acts as a cage to suppress the eruption. So in order to get a successful CME, you will always have to consider these two components. And our current understanding is that you will need to evaluate the strength of these two components. And if the expanding magnetic flux rope is stronger, then you will get a successful CME. On the other hand, if you have a very strong confining magnetic field, right, you will not get a successful CME. So I think that's where the trick lies. Okay. So on the sun, we do see CME trying to erupt, but then get stopped. So this movie, when I tested it, did not play, which is unfortunate. But what you would see if it actually played is that you see a filament structure, okay, as a proxy of the CME. It erupts upwards, then at midway, it gets stopped, right? You would expect the CME just to expand, but for some reason, it gets stopped, okay? So the reason for that, through numerical simulation and measurements of the local magnetic field properties, we think is because of the stronger overlying magnetic field. Okay, so everything proceeds as normal for the magnetic flux rope, but suddenly it runs into a wall, so it cannot escape. And I think that's the reason, one of the reasons to explain the failed eruptions. Okay. So this is actually pretty common on the sun as well. Okay, so we see this from time to time, and sometimes it can correlate with the largest flares. So in these cases, as the flux rope erupts upward, everything is normal, so you can still have the intense magnetic reconnection down below, right? And that magnetic reconnection will give you the solar flares, bright solar flares, right? But you will not have CME. So as you see, in this failed eruption mode, you will get flares, but no CMEs. And that is exactly what we see on other cool stars, right? So I think this particular picture of failed eruption will give you a sort of a template to explain what is happening on other stars. Now comes into a particular interesting examples that are relevant, that is relevant for stellar study, and that is something I did in 2015. So in 2014, October 2014, this particular active region image on the upper right, this is a magnetic field map. White indicates magnetic field coming out, black indicates magnetic field going inward. So this particular active region is the largest active region and has the largest sunspot group since 1990. And it is the most flare productive active region of solar cycle 24. So it has a huge amount of flares, okay. But most interestingly is that it amongst the 6 X-class flares, very intense flares, there's not a single CME. And if you recall the statistics of the CME flare association, right, for the most energetic flares, you should always get a CME. But here, 6 large flares, no CME. So this is an outlier, right? So at that time, we thought that if we understand what is happening to this particular outlier, maybe it will shed some light of why we can get field eruptions, because extreme outliers usually give you insights of the hidden physics, right? So what we found is that when you compare this large active region to the other smaller guys, okay, down here, that is also observed during cycle 24, which produced lots of large flares and CMEs. So the difference is that if you see these 2 large sunspots or active region polarities are pretty far away, okay. So that's one indication of the magnetic flux rope being less energetic. That's one of the indications. And also, because the active region is so large, you have a large amount of magnetic flux that is acting as the confinement. Okay, so there are 2 factors at play. One is the less energetic magnetic flux rope, which is the driving engine, and then you have a stronger overlying field. And the combination of 2 factors gives you a failed eruptions. So that's what we think is going on. Here's a cartoon indicating, just illustrating what's going on. Okay, so you have a magnetic flux rope, the cyan, curves trying to escape, and then when you have a strong overlying magnetic cage, if you see it that way, and that would hold the cyan magnetic flux rope back and would come down again. Okay. So because this active region is so large, and we know for other cool stars, the star spots are usually larger, right? So this acts as a perfect solar analog for stellar active regions with large flares, but no CME. So I think, by studying the sun and this extreme outlier case, that gives us a lot of insights of what is happening on other stars. And this picture has been actually, tested with solar MHD modeling tuned to model in the stellar regime. And it shows that when the stars have a strong dipole magnetic field, it is possible to have these large eruptions with strong flares, but no CME. Okay, so for the remainder time of the talk, I will go through some of the work I did recently, trying to establish a theoretical framework to explain why that is happening. And the theory I'm going to propose here involves a so-called torus instability, which is basically an ideal plasma instability that controls the disastrous expansion of the twisted magnetic flux rope. Okay, so this is actually an old theory. Okay, but what is important here is the background magnetic field. And especially interesting is the so-called background magnetic field decay index. Okay, what basically happens is that you measure the background magnetic field strength, B here, how it changes as a function of height. So if you approximate the strength of the magnetic field as a power law, this particular decay index basically is the slope of the power law. So when this number is large, okay, that means the magnetic field is decaying very rapidly with height. And that means, it is very easy for the flux rope to erupt. And when this number is small, that means the magnetic field decays slowly and you have a stronger magnetic field at higher heights, and it would be very difficult for the flux rope to escape. So this is the number of interest here, okay? And I'm going to show two different simulations on the right, okay? So when we have this background decay index, we can define a critical index above which it is easy for the torus instability to occur. And below that, it would be difficult for the torus instability to occur, right? And the height at which this this decay index reaches a critical value, usually taken to be 1.5, and everything below that particular critical height, we call the torus stable zone, okay? So the way we frame this problem is that if your magnetic flux rope resides in this particular torus stable zone, it is less likely for CME to occur. But for some reason, because of other physical mechanism, your flux rope grows a little bit, and if your apex breaks through this particular height, torus stable zone, then your CME could proceed. Okay. And the difference here is illustrated by the simulation. So for this particular simulation, you have a flux rope that is growing a little bit. However, the torus stable zone, or the critical height, is here. Okay, so it's very large. So the entire flux rope resides in this safe zone. So it is very difficult for the flux rope to erupt. On the other hand, if you look at the top one, it has a smaller critical height. Okay, so the flux rope grow, and it exceeds the critical height, then it erupts. So the differentiation of these two cases is the height of the torus stable zone. Now, what I propose is that the difference between the solar and other active star magnetic environment is such that for other stars, because the background magnetic field is strong, the torus stable zone is usually very, very high. So no matter how you build up your magnetic flux rope, it always stays in the torus stable zone. So it is very difficult for your CME to erupt. And on the contrary, if you look at the sun, the torus stable zone is usually pretty shallow, very low down. So it is pretty easy for a magnetic flux rope to reach this torus instability. Okay, so I'm going to skip this, but basically what it says is that for the previous events, okay, that I showed, for the failed eruption, it could also be explained by this particular mechanism. Okay. So what I did is I built a very idealized stellar magnetic field models to evaluate to the first order how big the torus stable zone is. And the stellar magnetic field model I built is a simplified version which contains two critical components. One is the dipole magnetic field that is basically characterized the background magnetic field, large magnetic field. And then, because the stellar CME and flares come from these star spots, I'm putting a small bipolar region on the equator, north-south symmetric. Okay, I'm running short on time. Okay, to mimic the sunspot or star spots magnetic field. Okay, So by varying the relative strength of the overlying magnetic field, the large-scale magnetic field and sunspot magnetic field, we will be able to characterize the the height of the torus stable zone. So what I did is try to use the observation to constrain these parameters. So I vary the star spots between 3 degrees to 25 degrees, and the dipole strength between 0 to 1,000 degrees, because for some of the more active magnetic stars, the background dipole field could be as strong as 1,000 Gauss, and some other parameters. Okay, let me skip through the actual numbers just to directly to the final results. Okay. So this is a diagram of the torus stable zone heights as a function of the star spots on the x-axis and on the dipole strength on the y-axis. Okay. So for our sun, the spots are usually pretty small, 5 degrees, and the dipole is only a few Gauss. So our sun only occupies a small region of the perimeter space. Okay. So in this particular case for the sun, the torus stable zone is quite small, okay, a fraction of the stellar radii. However, when you move into the other cool stars, which usually inhabit somewhere here, okay, and you can see the torus critical height can be as high as several tenths of percent of the stellar radii. Okay, so it's usually much higher than the active region size. So that explains why the eruption will be very hard to proceed on other stars. Okay. So I'm going to just go to my conclusion slides. Okay, and I think what I touched on is the fact that the stellar CMEs are quite rare, and based on what we learned from the sun, we propose that the magnetic field environment is quite different on other cool stars compared to our sun. And we've built a very idealized numerical model to explain why that is the case. And from now on, what we can do is to use these detailed numerical models built for the solar case to mimic or to simulate the eruption process on other cool stars. And that will be our next step. Thank you.
We have time for some questions. Hello?
Great. It was a wonderful talk. So my follow-up question is most stellar systems are binaries or sometimes even triple stars. How does that affect whether CMEs can be launched if you're in two heliospheres at the same time?
Obviously, we haven't considered that, but are there MHD models for stellar magnetic field interactions? If anybody knows, so I feel like in order to understand that, you will really need to build the magnetic field models of binaries and look at that per se. But I feel like the basic eruption mechanism, for example, the torus instability, or some of the triggering mechanisms should still be the same. It's just the large-scale magnetic field environment will be different. And instead of being one stars, you have a binary interaction if there's magnetic field interaction, and that will give you a more varying or more variable background magnetic field that only adds to the complexity. But I think the constraining physics should be more or less the same.
Thanks for this interesting talk and interesting possibility when the CME can be failed. That's certainly a valid case. But just want to say that when you say about active stars come G, K, and M dwarfs, and they can be old or young. So many different magnetic configurations, and that's why we take the ZDI images, and ZDI images give us global magnetic field, and the global magnetic fields of, for instance, of young suns show that they're highly dynamic. They show the very dynamic signatures of multiple fields. I mean, you showed the case of the dipole field, but the dipole field is a very, especially for younger stars, it's very a small well, it's only one, I would say, the only one configuration out of many multiple fields where this torus instability would not be working simply because the field is open. Okay, so that's why that was one question that I had in mind, because the sun shows failed CMEs, right? But let's say that according to Gopalswamy's work, then the cycle 24 shows more CMEs because the overall field is weaker, right? Than during the previous cycle. But again, it's not just about the total magnetic field, the total magnetic flux. It's the magnetic field distribution, right? So
I totally agree with you, and I did not get to show the caveat on my studies, and we're fully aware of that. Because on the sun, if you look at the star spots, okay, sunspots, it's so fractured, and there's lots of nesting, and the higher moments of the global field could also play an extremely important role. So that's why in the next approach, okay, the follow-up work that we are currently ongoing. So this is ZDI map actually of a star. If you basically take the solar, polarization observation and run it through the ZDI, this is the actual solar magnetogram, and this is ZDI map. ZDI map only gives the lower order. So that apparently cannot capture the full complexity. But we do have other tools that we can use. For example, we can run an ensemble model of stellar active region emergence, and then let it evolve using the so-called magnetic flux transport model. So we are capable of generating a large ensemble of magnetic maps like this, and then use the CME models of the sun to see what, to simulate what happens. So that will be our next steps.
Yeah, the magnetic flux the transport model works for our sun, because there's those small scale structures, but it cannot be applied for the active stars because they have large scale structures. So that's one thing. But I agree completely that.
Let's take some other questions and continue the discussion during break. Thank you.
So I'm curious if there are laboratory experiments that can be set up in a plasma chamber to generate something like a flux tube and then control the magnetic fields to cause ejections and lead to transport. And do those laboratory experiments inform or confirm these mechanisms that you're describing?
I cut that figure out, actually. There is quite a few numerical experiments, and one particular relevant experiments is done, I think, in the Princeton laboratory, where they actually produce these flex ropes where you can control the background magnetic field as well as the twist of the magnetic field. And they run hundreds of experiments and take a look of the two mechanism instability. One of them is the torus instability. So that they actually verified the theory of torus instability, although the critical height or the critical decay index is somewhat different in simulation compared to the solar case. Of course, there are many reasons why they're different, but I think it is generally agreed upon that torus instability is one of the main driver of solar CMEs.
But those are numerical experiments or laboratory experiments in a plasma chamber?
The laboratory one, what I was talking about in Princeton,
Fascinating explanation and very well explained. So
thanks.
But it seems the observational evidence is that you're not getting the absorption by H alpha. But even with the confined CMEs, the failed ones, are they confined in a place where they're just not cool enough or not large enough to be able to see observationally? That is, do they need to get larger and cool more as they go up for the absorption of H alpha?
Yeah, that's a tricky thing. It's not actually going back. But one thing is that you see that the flux rope or filaments undergo extreme expansions as they erupt upward. So for the sun, if you can think about it, the sunspot's size is only 5 degrees. So for the solar field eruptions, it goes up a little bit, maybe 0.1, 0.2 solar radii. It does not expand that much. So if you imagine it in the stellar case, it's not going to cover a large area. So the absorption would be too weak to, to be observed.
But observationally,
Yeah.
we should still be able to see it if we had the sensitivity to see
Yes, with
smaller.
enough sensitivity, I think it's a possibility. It's a possibility, but also you need the right geometry, for example, right?
Yeah.
So it's a lot of things at play, and because it's unresolved, so we can only, trying to guess.
Yeah,
So,
we're kind of spoiled by the sound,
yeah.
aren't we? Thanks.
Hi, Shunong. Thanks for the nice talk. So, assuming there's a lot of confined eruptions on the more active stars like M12, so I believe it's gonna influence the mass loss rate because you don't have the mass go out of the star. So then is that possible to see that from the stellar observations, that because they have the rotational rates slow down from the active star to the more solar like start. So have you looked at this kind of observational evidence to see that?
That's a good point. I have not done it personally, but one of the reason people are talking about there should be fewer CMEs compared to the solar scaling is the angular momentum argument, because they actually try to do the calculation to extrapolate the solar CME scaling. So if you assume all the large superflares have a CME, what would happen to the rotational rate? And turns out that the angular momentum loss in that case is hundreds of times higher than what it is actually happening on the stars based on the rotational modulation, rotational observation. So if you have lots of that's one of the explanation. If you have that many CMEs, the stars should be rotating much slower than what we are observing now. So that's one of the argument they were using. Yeah.
Any other questions? Yes, one more minute.
Yeah, that's a comment to Monk. And well, actually speaking, yes, you're absolutely correct. That would, you cannot simply take and approximate what's going on. But again, so it depends on the age of the star. And during the, the younger age of the star, it will more dynamic, more open, the more, so more ejections will occur. But, at the older age, the situation becomes different and age dependent. And just last comment is that when you said that our sun is unique, and well, I wouldn't agree that it's unique. It's common G-type star. If you look at the stars and the stellar observations with rotation rate between 25 and 30 days, show that those stars show super flares at the rate of our sun showed of the historically over the last 8,000 years. It showed 8 super flares, as I was talking about. 775, it's one of them, and 7 more already been discovered. Okay, so we don't know our sun really well.
Yeah.
So
I think what I was trying to get at is that our sun has a relative magnetic field compared to the whole population. So it's on the weaker end. That's what I meant.
Yeah. But all stars of the same rotation rate have the same total unsigned magnetic flux. That's all.
Okay.
Thank you.
Thank you.
Our next talk is a virtual talk. This is going to be given by Ankush Bhaskar, who is also actually a steering committee member. Unfortunately, couldn't be here. He's from Space Physics Laboratory, ISRO Vikram Sarabhai Space Center in Trivandrum, India. The title of the talk is Planetary Space Weather Way Forward. Ankush, are you online? Oh, right there. Awesome. We can't hear you. Are you muted? Can you restart? We can't. Just try to speak even without the slides. We can't hear you. No sound at this end. Do we need to restart here? We still don't hear you. Do you want to restart? What's going on? My WhatsApp out. So he's not receiving. Can you send the Zoom chat? No, because he's connected to this, right? No. So let's make some executive decisions, and we'll go to the second talk and give him time to restart and communicate with him. So sorry for the situation. And let's start with our student speaker, Caitlin Go. Thank you. School of Physics and Astronomy, University of Leeds, UK. And the title of our talk is The Martian Upper Atmosphere on Intercomparison of LMD Mars, GCM Simulations, and MAVEN Observations. Do you want to use
I'll probably stay here. I can't move around very much, so. Is it the green button to... how do you switch the slides, sorry? Green button. Okay, right, cool, thank you. So hi, I'm Caitlin Goff. I'm a first year PhD student from the University of Leeds. My supervisors are Dan Marsh and then John Plain and Woohoo Feng. So in this talk, I'm going to be discussing the Martian upper atmosphere through an intercomparison of LMD Mars PCM simulations and MAVEN observations. So I'm going to be kind of going through the work that I did as part of my master's project. I'd also like to thank the organisers of the symposium for the opportunity and the funding to come and present my research. And also in the spirit of open science, I just wanted to add that all of the figures I'm going to present today were made using Jupyter Lab and have been uploaded onto my GitHub. So firstly, my master's project focused on magnesium plus ions. So NASA's MAVEN spacecraft entered Mars's orbit in 2014, and it was the first mission that was dedicated to measuring the upper atmosphere of Mars. Before MAVEN, only metallic species in the Earth's atmosphere could be directly measured. And the results that I'm using are from the imaging ultraviolet spectrograph. And this instrument has detected a persistent layer of Mg+ in the upper atmosphere. The interesting thing about Mg+ is it has a long lifetime, longer than the ambient ions in the atmosphere. And this is because it's unable to undergo dissociative recombination reactions with electrons. And this means that it can be used as an important tracer of dynamics in the upper atmosphere. So this is the models. This is the LMD Mars planetary climate model, and it sort of simulates the atmosphere from the surface up to the exobase. And on the left is a sort of scheme of all the different chemical and physical components that go into the model, and on the right is the magnesium chemistry scheme. So a meteor input function is used to simulate the input of magnesium into the atmosphere, and then there are 7 neutral and 8 ionized magnesium species that result in a total of 42 reactions. So this intercomparison of MAVEN observations with the LMD simulations is important for understanding the variability of this Mg plus layer. So first I'm going to look at the diurnal variation. So as you can see, the model captures really well the peak at 6, but not so much the vertical transport of Mg plus. We can sort of ignore below 80 kilometers because the data is not very reliable because the IUVS instrument becomes dominated by solar fluorescent scattering. So sort of first off, we can kind of eliminate the fact that this would be caused by photoionization because we would expect the peak to be at 12 and it's at 6. We also plotted the mixing ratio and it didn't show the same diurnal variation. So this would suggest that this is an effect of chemistry. Plain et al. 2018 calculated that there is a 5-fold increase in the mixing ratio between 95 kilometers and 105 kilometers, which would suggest that this effect is due to tidal descent during the night, and this is further evidenced by the observed temperature increase between 4 and 6, which suggests a diabatic heating of this descending air. So next, looking at the seasonal variability. So here I've split the seasons up using solar longitude. So LS 60 to 120 is the northern hemisphere summer, and 240 to 300 is the southern hemisphere summer. So first of all, we can kind of see that the peak altitude during the northern hemisphere summer is at about 90 kilometers, but this shifts up to about 110 kilometers for the southern hemisphere summer. And this is because of the increased amount of evaporation of CO2 ice increases the atmospheric pressure and therefore increases the maximum altitude at which a pressure of 1 microbar is achieved, which is the pressure required for the magnesium to ablate. Also, the model captures really well this depletion of Mg plus during the southern hemisphere summer. And this is as a result of an increased evaporation of surface water ice, and this leads to an increased sort of concentration of atmospheric water vapor and a conversion of Mg plus to MgCO3 H2O6 clusters as sort of depicted by the chemistry scheme I showed earlier. And this figure here just shows this anti-correlation between the column abundance of water vapor and the column abundance of Mg plus. So finally, looking at the latitudinal variability. So the top panel here is the meteor input function, so where the magnesium is injected. The middle 2 panels show where the sort of latitudinal variability of the Mg plus layer for the MAVEN observations and the LMD model, and the bottom panel is the meridional winds. So this shows that the latitudinal variability is governed by meridional winds and then also where magnesium is injected. So just to kind of have an example, for LS 60 to 120, we see that there is the biggest amount of injection in the northern, the northern hemisphere, but then this becomes distributed across both southern and northern latitudes. And we can see by the plot for meridional wind that that's due to these meridional circulations towards the South Pole. This is because during the southern hemisphere winter, there are extreme cold conditions at the pole, and so there's a deposition of CO2, which induces these meridional circulations and drags the Mg plus across. So in conclusion, MAVEN has been measuring Mg plus in the Martian upper atmosphere since 2014, and this long lifetime of Mg plus means it can be used as an important dynamical tracer. The diurnal cycle peaks at 6, and this is due to the downward transport of air during the night. Seasonal variations in the atmospheric temperature alter the altitude at which meteoric ablation is occurring, and then therefore affects the height at which the Mg layer is throughout the year. And the higher temperatures around perihelion will reduce the Mg plus in the southern hemisphere, and this is due to this increased evaporation of surface water ice and the formation of these magnesium carbonate clusters. And the latitudinal variability is determined by both the MIF and the meridional winds. In terms of pointing towards future work and things that I might be looking at as part of my PhD, there is an absence of an observable layer of neutral magnesium. I made this plot on the right, so the grey line shows the LMD prediction with latitude, and the red line is the IUVS detection limit. So this kind of shows that we would predict that we would see a magnesium layer, but we don't. The only time we did was with the close passing of the comet Siding Spring in 2014, but it showed that the neutral magnesium was depleted much faster than we thought. So that shows we've got some sort of missing gaps there with the chemistry. So that would be something that'd be interesting to look at, and this could be done partially through modelling this close passing of this comet in 2014. And then we also want to include the other ablated metals, so sodium, iron, and silicon. And then I also kind of want to investigate the observed sporadic metal layers that have been observed in the upper atmosphere. So thank you for listening, and I'm happy to answer any questions.
So we'll take the questions together after the virtual presentation. Cool. Thank you very much. Ankush, are you ready? Can you hear? Hello? Okay, we are going to bring up, yes, we hear you now, yes. So let me read out the title of your talk, Planetary Space Weather Way Forward.
Okay, this is okay. You can hear me, right?
Yes.
Can you hear me, Eddy?
Yes. Yes.
Yes.
Where is his presentation? That's with him?
Hello.
Can you hear us?
Yes, Mika, I can hear you. Can you hear me?
We see you, we hear you, but we don't see your presentation. Yes. Yes, so you can go back if this, I don't know if this is the first slide, but you can go back to your first slide if you need. Yes, we do.
Sorry for that. You didn't hear anything, right? What I said. Fine. Yeah. First of all, sorry I couldn't make it for this symposium, but I am seeing a very nice brainstorming and very beautiful lectures going on. I really miss it. So I'm going to just talk about some perspective level talk here because not many good talks already.
planetary atmosphere and magnetosphere, but CIRs generally dominate in the descending phase and they will impact the planet. Whereas X-ray and UV keep changing during the whole solar cycle, and GCR, which is anti-cold grade, already today, on a first day, like I already mentioned, GCR fluxes are enhanced during the low activity and they are hazardous, like that is the radiation impact. So that also comes in picture where, what phase of the cycle we are in. So this is just represent like two like planets, Earth and Mars. I'm taking because they are completely different. Here, Earth has a very intrinsic magnetic field, very complex magnetic field. We know a lot because that is the closest to Earth. We have many missions which have measured and still measuring plasma environment around the Earth. So our understanding has become more complex. More than just a general picture, we know more detail, and still there are unresolved problems in this Earth's magnetosphere. Whereas if you look at the cartoon here, which is a Mars, which is an induced magnetosphere, so it doesn't have like very complex type current systems we do see, and radiation, strong radiation based environment like Earth it doesn't have, and it has different like ion pickups coming in picture. Mass loss is very strong due to the solar wind, which will play a key role. So I will just go ahead. So this is what we have now. I think as to study the exoplanet before, we have a closest observatory Earth and nearby planets which need to be very well studied. So we can treat them as exoplanet and get lot of information from them, which we can actually analogously apply in certain conditions to exoplanet. So here we can see how the magnetic field for different planets we have, it drops as we go outward from the sun. Then interplanetary density drops, magnetic field drops, so their impact is different at distances. Plus internal dynamics of these planets, because Uranus, Saturn, this Jupiter, they have their own strong magnetic field, and there are satellites which are interacting with magnetosphere, causing auroras, and that comes in picture. So these are the typical examples we have in our own solar system, which are very important to study for exoplanets. So as we go to exoplanet, already this picture type or video is shown by Valdemar today morning. So this same picture we can see now, there are so many exoplanets. So this is beautiful thing to know, like some time before we knew only planets in our own solar system, and now suddenly we have 5,000 plus exoplanets known populating the galaxy, and definitely many more will be there. And not only this is a very advantageous because we cannot go back and study our Earth in a different time, how it was evolved during solar activity, or actually we cannot have all the samples, whatever all the plasma conditions or stellar conditions of planet near Earth. So the universe provides us opportunity. There are thousands of planets in a very different condition, very different space weather conditions we'll be encountering and studying. So this gives us an opportunity to probe the exoplanetary environment. So this is what now, as we progress from Earth to the planet and then exoplanet, so our understanding we are trying to analogously put from Sun to the planet, Earth to planet and exoplanet, but also there is a reverse information flow in this. Whatever we learn from exoplanet also can be applied, can advance our understanding in a planetary space weather and even Earth's space weather impact, because there are few things which we cannot study at Earth. Maybe this huge collection of different space environments around exoplanet will give insight. So this is what I feel what we can learn about the exoplanet. Actually, it's an ensemble. We get few thousand and a variety of conditions. So different stellar condition, different star evolution time, different type of stars, different stellar wind conditions we'll be encountering. So that advantage we have, and then we have like we can go back like Earth future, or like we cannot travel Earth's future, how the space weather will evolve, or past we can have some understanding from ground-based data, whatever we or geological timescale data, whatever we have. We can understand something about Earth's past. But this ensemble of this all few thousand exoplanet will give we will able to actually do time travel in different epoch of stellar activity, and gain more understanding what happened with the Earth, or and what will happen with the Earth in future also. So also diverse star planet interaction, as I mentioned already, this gives a very different star plasma condition, star condition, star planet interaction, star planet satellite interaction, huge things are means once we get more data, we'll learn in diverse interaction scenarios. And unknown territory, this is one thing we'll have more possibility in unknown physics, unknown phenomena we may encounter. Like a simple example I think of, like subalfinic regime of the sun. If you look at the sun, we don't have any planet in subalfinic region. Mercury is outside. So first time PSP will be sampling already sampling the subalfinic region, and this understanding actually what we learn from the Earth can be also used to look at the exoplanets, because there are many exoplanets which could be in subalfinic region, and their space weather impact will be completely different. So this is like going to open up a different laboratory for us. So what are the open, like I'm trying to list just some problems from space weather around the Earth, which could get some insight from the exoplanet or stellar activity by studying other planetary systems. So like extreme events like extreme solar flares and CMEs, how often they are, and this is very difficult sometimes to probe this question, even though we have like a few, like 5 or 6 like extreme events recorded in tree rings and all. So some information we have, but this like suppose we study G-type star and we have a few thousands of stars and study their stellar activity, like similar like sun-like stars, we can get idea how common are these extreme events, and maybe we'll able to even predict or give a probabilistic estimate how often they happen on the Earth. So that is one we can learn from these. And another is how does mass loss rate is controlled by solar wind for planets, and for induced and intrinsic magnetosphere that will be different. This estimates, because shielded magnetosphere, some observations show, means some study shows that it protects the atmosphere. Some shows that okay, it can actually enhance the mass loss rate also. So this also part will be important in exoplanetary terms also. But still, we have to still get hold on this exact estimate for our own solar system planets. So how this process spaces evolve around Earth, that's what we can even learn from other exoplanetary and stellar environment, which I mentioned. So here we can see the most, I think this is the largest super flare observed on TIC 260, this NCAR star, around 10 to 36 or something. So that we can see what possibilities we have in front. So there are open problems in space of exoplanets, which also means our own understanding from Sun may help. No in situ measurement possible at present for these exoplanets. We are too far to go there, at least not now. In future, definitely. I don't think we'll not go there, but we'll go in future, and then we'll get real measurements, in situ measurements from there. But at present, we have to really rely on remote sensing and modeling of these exoplanetary environments. So the another problem, we have properties of stellar wind around the exoplanet. Once again, these are all like model based or some somewhat observation, very few observations we have. So exactly still we don't know exact stellar wind conditions if any some exoplanet is going through, because no measurements in situ. So space weather impact on exoplanet atmosphere. This is still evolving. Like we are seeing some already presentations on that, how the atmosphere it affects SCPs will affect differently. Solar wind will affect differently. CMEs are there, X-ray enhancements are there. They have chemical changes and all happening in the atmosphere. So that is still I think we have to learn a lot about in this. Also, this our understanding, we have limitation one, sun type stars, we can apply to up to maybe sun type star, maybe we can rely on that 100%, okay, that works, but as soon as we deal with other types of stars, now I think we may have a lot of uncertainty because validation is very tough in that. Last point I want to just say impact on habitability, because this is yeah, Vladimir already gave a beautiful talk today. I don't want to talk on that part. So yeah, this is a key problem, key thing, and maybe important for a biological life evolution of a given planet. So what we do now, what we need to
So
do as
Ankush,
spring. Yeah,
I don't know if you have many more slides. You're pretty much close to the end of your time. So if you can wrap up, thank you.
okay, thanks. Last slide. So what we need to do is identify key area questions from near space weather and exoplanetary space weather, which have which are complementary to each other, and both information from both can help to resolve this question. Then create a task force with different expertise to address those questions, identified question in next 3 to 5 years, which may need modeling efforts or some observations or some mission planning. And then utilization of open data science and citizen environment, I don't have to say how important they are. Already some talks were there. And yeah, that's it. Thank you.
Thank you very much. And I think we'll take questions for both Ankush and Caitlin at this point. If you can come to that microphone out there, and Caitlin has a microphone to answer also. And so Ankush, please stay online. There might be questions. Yes, please.
My question to Caitlin. So very nice talk. It's very interesting study. My question is about the. I see that the the most of the observations show that magnesium plus appears much lower, about like 60 kilometers. So what kind of input did you use? Did you use the input of the some precipitating electrons, or it's only meteors, or what was your ionizing factor of magnesium? What was your input to the model at the upper boundary?
So the meteor input function was what was inputted into where the magnesium was injected. And then it has like the full chemistry scheme, which obviously affects things as well. But I'm not sure about other, is there any? Yeah.
So so you have your, I would imagine, extreme UV. Oh, sorry, yes. Yes.
In the observations, a lot of that magnesium in the lower part is an artifact.
Yeah. So the peak is at like 90 kilometers and then higher. But obviously there's a lot of like noise below like 80 kilometers. So we can't really trust the observations below 80 kilometers.
I see. Yeah. So you have your input in terms of the UV emission, right? So probably because ionization energy is about like 7 electron volts or something like that. So yeah, so that basically, okay. So you have the is input and charge exchange. Yeah, okay. So did you use solar minimum or solar maximum, or I mean the flux?
I think it's actually it's the same as this. It's the right. We've done it over how many years? Martian years?
So the LMD run for that is 4 Martian years. Yeah.
Very nice. Thank you.
Thanks.
Hi, this is for Ankush. Hi, Ankush. Nice talk. So my question to you is, when you really want to understand the space weather of exoplanets from our understanding of the space weather of Earth, but most of the exoplanets that we got are close in. Where I mean, if you really look at Earth doesn't impact back to the sun. Most of the impact is on the Earth because of the sun. But when you really talk about close in exoplanets, the interaction is like both ways. So in those cases, like understanding the space weather just based on Earth, do you think that's a like correct approach?
Yeah, that's what I mentioned. It's always may not be true. As we take whatever we understand space weather around sun, we can exactly apply. to other planets, because as some planets may be in solar alphanic region and their interaction is two-way, right? One planet may be affecting. So yeah, we have to see. It may not be always true. We cannot go one exactly copy paste there and apply things. We have to see the given conditions.
Okay, thanks.
Yes.
My question is for Ankush. You know, you in your presentation you were talking about space weather. So as an ionospheric physicist working on Earth, I'll look at it in terms of the impact on the Earth system. But now, in the last slide, you raised some questions with regards to we're looking at space weather on Earth and seeing how we can use the space weather on Earth to solve problems in other planets. And you raised some open questions. So my question is, before we address the issue of the open questions, in Earth, we have forcing from above and below, and we also look at the mechanisms that are arising from all these things. So in those exoplanets you're talking about, are you also going to compare the mechanism arising from Earth and compare it with the possible mechanisms in those planets? Because my understanding of these planets is that they are made up of different gases and they have different chemistries that are taking place. Thank you.
Yeah, that is another, like you have forcing from above and forcing for below. As for Earth ionosphere, we can think of it's getting affected by solar wind forcing, but not only that, even lower atmosphere, like gravity waves and all, going and depositing energy in the ionosphere and changing the environment. And similar thing may be happening for Venus also. There are some observations for like different layers of ionization are observed, and some gravity wave perturbations may be possible even in Venus atmosphere. So not everything as compositions is different, definitely. May not be exactly everything we can, as I said, analogously look at, but there are some fundamental processes which may be really key. We can really analogously apply to them. Like as I said, gravity waves are impacting on Earth, but even there are now some papers showing gravity waves impact on the Venus, which is a completely different like composition, right? So similarly can happen for exoplanet.
Hey, Ankush, Kalpesh here. I have a question about we have certain missions that covers the planetary atmosphere and that can help us to dig out the information regarding the evolution of this global structure, like CME, that we have Messenger, we have Venus Express, we have Marvin for the Mars. But do we have that certain amount of in situ observation in an outer planet to study these phenomena in a distance of again 5 AU, 10 AU? So because the certain things that we observe on the earth, such as alphanic region in magnetosphere, for Bush degrees in, so that we are observing in the other planets also. So do we need more in situ observation for the outer planets to probe these structures there?
So you, outer planet means I feel you want to talk about solar wind structures, right?
Yeah,
At
yeah.
5 AU or something.
Yeah.
So if that is the thing, it's okay. Actually, as a Henry physicist, you want to have everywhere measurements, right? So that is going to what dream for us. But yeah, we don't have many measurements as we go away from the sun, definitely. But there are some number of studies using Voyager data, like evolution of CMEs and merging of CMEs. Those are called JMRs, I think, giant merging interaction region or something, JMI interaction region. Yeah, even cosmic ray studies have been done, but yeah, we have a limited because not many probes have gone so far, right, away from solar system. But future we need to think of that also, like after Voyager, what we have going back now after Voyager, if we lose, then we don't have anything follow-up stuff. So those type of things we really need to think to study the outer hemisphere and its impact.
Thank you.
Any other questions? If not, let's give another round of applause to both the speakers.
I don't have a question, but I do have a couple of announcements before everybody disappears. The first announcement is steering committee, you know who you are.
On the third floor is where we have our meeting today, now. Um, if you haven't been in the boardroom, if you go up to the third floor, you walk out, you walk around the gym area, it's on that side. So if you get to room 304, 306, just look across the road and you'll see it doesn't have a number on, but just look across. It's just on the other side of the gym. So please gather there for our steering committee meeting. There has been a request to change the agenda for tomorrow morning, so we're going to have breakout sessions first tomorrow morning so that our groups can finalize their reports and finalize working on those. And then we're going to have the report out, look for the changes on the website tonight. But there is going to be a change tomorrow morning in the way we do things. And I know we have one or two other announcements. Vladimir, you wanted to make an announcement?
Yeah, thank you. So just want to inform you about this upcoming, in case if you're interested. So just yesterday night, I received a email from the Science Organizing Committee that my session, Super Flares and Eruption Events from Active GK M Dwarfs and their impact on habitable environments, that basically is going to discuss all those issues, that's a heliophysicist, astrophysicist, planetary scientists, climate scientists going to get together for the 1 or 2 days, to discuss those issues. Modeling, observations, and modeling. So please, this is the largest astrobiology conference that occurs every 2 years. Okay, so this next year will be in Rhode Island, in Providence, Rhode Island, May 5 to 10. So for the full week. And so it's called Astrobiology Science Conference. This is very enlightening conference that will enhance your horizons of habitability from astrophysical drivers all the way to biochemistry. Yeah, thank you. If you have any questions, I'm available.
Yes, please.
Since we're talking about sessions, so TESS was mentioned at some point, or maybe that was my imagination, but there is going to be an open science town hall at TESS. It's not on the schedule yet because they made it a town hall. Maybe they liked my format, who knows? But it'd be interesting to carry the conversation about the open science things there, because there's going to be short presentations and then discussion. So you saw how I led the little half-hour thing yesterday. Imagine that on a larger scale. So nice to see your faces there and hear your thoughts.
So, Rebecca, can you just give the dates and place of the test? And okay, so this is
yeah. So
and maybe we can put this on the Slack for everyone. For everyone, whatever we are discussing, that's for general information. Please include this on the general hashtag on Slack.
Maybe that's where I should even say. But so I think registration is actually closed for TESS.
I do not.
Oh, okay. Thank you for that correction. So yeah, okay. So registration is open, but you can't submit anymore. Life. Okay, but it's going to be in Dallas, Texas, in the Path of Totality. So that extra level of coolness. April 8th, I think it starts the night before, but me and dates right now, and it goes through Friday. So you get all of Monday for the solar eclipse, and then there's 4 days of science stuff. So maybe I should put other things on.
So I had an interesting conversation with Lisa Winter before the current session, and in doing some subsequent web search, I found a Dear Colleague letter, and there is an opportunity that I shared in the general Slack for digital infrastructure focused meeting support. So if any of these working groups are interested in getting together and talking about, data interoperability and things like that, it looks like NSF has a program to support some funding for that.
Any other news? Do you have any more information? You guys will be, yeah. Okay. Okay. See you at 1:30.
Just want to remind everyone, the working groups are still going to be in the afternoon at 1:30 in the same places. And see you then.